Our speaker this year is really an exceptional individual. I've had a chance to, he's actually staying with us, so I've had a chance to get to talk with him a little and get to know him. When I try to decide on the speakers to give this lecture, I go through a pretty rigorous process, and I print out all their academic papers, and I get a sense for their body of work before I invite them. And this year it was really hard because his body of work, if you looked at the binder, it's about this thick of papers, and that doesn't include his books. I tend to read the papers instead of the books. But he has the range and the scope of his contribution, to say nothing about the depth of it and the originality of it. It's really quite an incredible contribution. And I know many of you are familiar with quite a bit of his work, and it's really very, very unique because it spans many, many different disciplines: economics, cognitive science, healthcare, finance. There's almost no area where his expertise and his contribution it's just been unbelievably significant. And I think on a personal level, what has helped me, this whole idea of cognitive illusions that we are subject to as clinicians, we have a lot of cognitive illusions, and how he's taught us how to overcome these and deal with them, especially in the framing of our conversations with patients about risk. It is, for those of you who have adopted this in your practice, it is so powerful, so impactful to us as clinicians in learning how to frame conversations with our patients. So it's a tremendous honor to have you here, Gerd, and I think you're going to find a very friendly audience. Please give a warm welcome to Dr. Gegenrenzer. If you can appreciate the change that Dr. Gegenrenzer has made in the field of cognition, imagine what he did. He went up to a couple of Nobel Prize winners, and he said, "You know, I don't think this heuristic and biases thing is really accurate. I don't really think you've thought it through very well. And here's why. And then here's the proof." That takes some serious cojones. And he had the courage to do this. And he's had a tremendous effect over this whole heuristics and biases program that had really taken over cognitive science and the academic establishment. And I'm very happy to see that he's had a huge effect in making people question this whole thing, that we're not Bayesian in our thinking. So his next presentation is on this whole heuristics, and hopefully he'll be able to communicate it really well. So, Gerd.
So, in this lecture, I want to introduce you to the research how to deal with uncertainty. So far we talked about situations of risk where we do have the numbers fairly more or less well, and now we're talking about uncertainty. And one tool is heuristics, and that's what I will explain and talk about. In general, the message is that in many situations, you can do better, meaning better predictions, better diagnosis, when you don't use too complex methods, but simple enough. And the title of the talk is Simple Heuristics That Make Us Smart. It's taken from a book that my researcher and I published in 1999. And it has the motto of Isaac Newton, saying, truth is ever to be found in simplicity and not in the multiplicity and confusion of things. And let me start with 3 examples. Each of these examples is just a kind of existence proof that in many situations you can do better with limiting yourself to the few most important variables and just ignoring the rest. And as a sideline of this is that simple heuristics are not what you read in Kahneman's book, Thinking Fast and Slow, so always the second best thing. No, they are often better than what he thinks is always good, without evidence. So let me begin with 3 examples. A few years ago, I gave a keynote at a big data conference in Munich. There were 2,000 business people. There was one of the major proponents of big data, Victor Meyer-Schönberger. He has written a bestseller and co-authored a bestseller called Big Data. And a third person. And I gave a talk on the question, where can we be confident that big data is actually good and better than what we already have, and where this is not the case? That was my question. The Professor Meyer-Schönberger's question was, he had no question, he had a message that more is always better. And he showed slides where you had only the word more, and so it went on. That's convincing evidence, isn't it? So, as you may have been aware, much of big data is a big business and goes with anecdotes without any evidence. So the key anecdote that was proposed by my co-speaker here at this big data event was Google flu trends. So you may have heard of that. In 2009, there was a Nature article proposing that Google has developed a methods, an algorithm that based on search terms can reliably predict the spread of flu and influenza-related diseases in the US and anywhere. That would be a good thing, and predict faster than the CDC, so the Center for Disease Control, because it takes them a week or 2 to get the data from the doctors and so on, and it would be useful to do this faster, which is a good idea. Now, Google flu, explained that to you because it's a wonderful case to understand when big data works and when not. So Google flu, the algorithms, which is a business secret, which we do not know, but it's probably nothing but a linear equation. And with, I think, 45 variables selected from 100,000 of search terms. And they used 10,000 of models. And have done a mixture between data fitting and data prediction in the years before 2009, which is not really transparent, so I'm not making a judgment, but data fitting is always a problem. And as you know, the flu is high in the winter and low in the summer, but the data published, it fitted the curves very well. And then something happened that's unusual for big data, namely Google flu trends actually made predictions. Most of the big data I've seen is only after the fact. So big data is very good in doing after the fact. That's called surveillance. So to find in your history whom you met when and so on. That's very good. But the issue is here, is it also good in prediction? And as you know, prediction is hard, particularly if it's about the future. And in 2009, they started to predict. The problem was that, as you may remember, in the summer of 2009, the swine flu kicked in. And it was in the summer, not in the winter. And the algorithm was calibrated on years of summer, winter, down and ups, and of course failed. It's like a black swan, a little one. Yeah? In general, an algorithm can usually not do more than hope that the future is like the past. That's it. In particular, if it's fine-tuned algorithms, then it's even more problematic if the future is different than the past. So it missed that. Then the engineers from Google tried to adjust the algorithm, and it worked for some while, and most complicated algorithms work when nothing happens. But if something happens, they overlook it. That's the problem. And then for 108 weeks of predictions, they overestimated the actual doctor visits, the flu-related doctor visits, 100 times out of 108. That's a problem. And one of the reasons is probably causal knowledge. So the algorithm can only go by associations. And what happened is that not only people who had symptoms entered search terms to find out about flu and swine flu, but also people who were just curious and had no symptoms. And the algorithm cannot distinguish, so it overestimates the factors. Just see that. The point is that between 2011 and 2013, it was very clear that they're not going to be able to fix that. And it was in 2014 when I was on this podium, and this major proponent of big data brought Google Flu Trends as the showcase for the success of big data at a time where it was clear it hasn't worked. But there were 2,000 businessmen, and he is a very convincing speaker with slides like more, and complicated algorithms and stories about the success. And after we had given our talks, there was a TV moderator who was kind of this moving moderator, and who asked me what I think about the talk that I just heard. And I thought I'd just tell the truth. So what you had heard, and the audience was impressed by this big data performance, what you've just heard is the half-truths. You heard everything that happened till 2009, but not what happened in the last 4 and 5 years. And I tell you the rest, which I just told you. And I gave in detail how this overestimation worked and why the algorithm didn't work. So the moderator, his movements got less and less, and the audience was quite quiet. What's happening though on the stage? And then he, of course, asked Victor Meyer-Schönfelder, now what do you answer to that? And I'd given him lots of details he could have taken on, but he was very careful. He only said, Professor Gigerenz and I have different opinions, and the future will see who is right. And everyone noticed that they cannot respond to any of these things. And the future showed the algorithm was buried. But I think he's still going around and telling the success story. Like the Target story was another story. You know that one? Target, sure. The ideal of supermarket where the only thing you have to ever go anymore, and so. And they were sending the story that was publicized by Target was that a furious father came to the Target store complaining that his 15-year-old daughter got bonuses for baby clothing and baby things. And then a week later he came again and apologized, and he had found out that his daughter was pregnant. So the idea big data knows it first. Again, it's a story. There's no evidence there. So if Target sends every 15-year-old bonuses, then you have a hit rate of 100% and a false alarm rate of close to 100%. So just the point that I want to make here is now the following. Studies, when it was shown that all these Google flu trends, big data algorithms don't work, studies looked carefully what would work. And they found that a very simple heuristic predicted better than the entire big data thing. The heuristic was just look at three things, namely the influenza-related doctor visits 2 weeks ago, where one has data, and those 3 weeks ago, and for the 1 week ago where one doesn't have data, one takes the value from last year. That's it. No big data, very simple, predicts better than Google flu trends. First example. Second example. So dizziness, nausea, vomiting are among the symptoms of what's called acute vestibular syndrome. But in some cases, in rare cases, it's a dangerous stroke. How to tell? How can doctors find out whether the patient has a stroke? Now, a popular method is to take an MRI. The alternative is a very simple procedure. It's a so-called bedside examination. And it's called the HINTS, H-I-N-T-S examination, where H-I stands for head impulse and N for nystagmus and so on. It is a simple sequence of a few tests. And for instance, the head impulse tests, so the patient is instructed to stare at the nose of the examiner. And then the examiner takes the head of the patient and moves it quickly. And the patient is instructed to keep the gaze on the nose. And patients with stroke cannot keep it, so they have to correct afterwards, and you see that. A study showed that among 76 patients, the MRI missed, as a patient with stroke, the MRI missed 8 of them. The simple examiner, just looking on this one variable, missed none. It had one more false alarm, but that's the minor problem here. So the HINTS examine is something that a skilled doctor can do, and it saves time, saves money, and is better. And it's also, of course, in that situation, a CT is even worse than an MRI. So that's a second example about where we can see that less can often be better. Certainly for the patient. If you want to make money and doing MRIs, then it's better for you. Third example, the Ottawa-Enkel rules. So imagine a man injures himself while jogging and is hurried into the emergency department. It could be a fracture. To find out, most patients undergo X-rays, even though only few have a fracture. Now, a team of doctors at the Ottawa Hospital developed a set of simple rules to find out whether an X-ray is needed or not. And it requires the patient only to make 4 steps and ask whether it hurts on a certain position or not. A review of 32 studies showed that the Ottawa-Enkel rule can correctly detect fractures in more than 98%. So like the bedside examination, the HINTS one, it can also apply everywhere in the world. You don't need high technology, and you do it faster, and it's highly reliable. Now, there is a wonderful letter by a Californian doctor in a medical journal on the Ottawa-Enkel rules. He said, basically, in Canada, you can do that, not here. Namely, the reason, he said, why we take X-rays is legal and not medical. Better buy a machine, it costs you 40,000 or 50,000, but a legal trial where you lose or win costs you anyhow at least half of that. And just X-ray every patient and don't use any of these simple rules that work better. That's the topic of defensive medicine. So these three examples show that there's a potential out there to use simple, effective rules. Or, in other words, in the hints examen, if you identify a powerful variable, like the fact that a person whose head you twist has to correct afterwards, while a normal person does not, and that this is an example of one variable that is more powerful than an MRI. And part of the research we are doing is to systematically study where simple heuristics work and where they do not work. In some situations, you need complicated things. And that's also the topic of this lecture. So, one word before I start on medicine and big data. So Google Flu Trends hasn't worked. The Microsoft pancreas diagnosis that I mentioned before, nobody heard anything anymore besides the misleading statistics. Then you might say there's IBM Watson, who won the Jeopardy contest. That's a great achievement, but again, it's a game. And artificial intelligence and big data are good in games. So Go, chess, that's admirable progress. But the question is whether they can deal with the real world, where there's uncertainty, where the future is not necessarily like yesterday, and where swine flu can happen, and such thing. And IBM Watson had an alliance with MD Anderson, and MD Anderson has by now quit its contract with IBM, and they seem to have found out that Dr. Watson is not better than a regular doctor, just more expensive. They spent allegedly $62 million to find that out. And I also know of some IBM engineers who are embarrassed about what their PR Abteilung tells about Watson's abilities. But it's a business model. IBM Watson has meanwhile called the Donald Trump of the AI industry. Same things happen outside the medical area. You may have heard of the COMPASS algorithm. So in the US, more than 1 million people, like defendants or people who are already in a jail and hoping about parole, are subject to an algorithm. It's again a business model. Nobody knows exactly how it works, and which measures lots over 100 of variables and gives you a probability that you, the defendant, will commit another crime in the next 2 years. So imagine you're a judge and you have to decide about a sentence or about a parole, and then it says, 87% chance that you will commit another crime. Maybe you don't get parole. So we do not know about that part, but many judges will not be willing to stand up against these kind of algorithms, which they don't understand, nor does the defendant understand. And that's a wonderful situation. Nobody understands it. And it's legally that nobody understands it because it's a business model, but it determines our lives. And from 2000 on till today, more than 1 million Americans have been subjected to this COMPASS algorithm. Nobody had asked how good it is. People appear to believe in algorithms, particularly if they're complex and you don't know them. And in 2018, this year, the first study was published, which had looked at the question, how good are these predictions? And even you don't know the algorithm, you can find about the actual cases, whether they actually committed another crime in the next 3 years or not, and so on. And they found that the algorithm gets 35% wrong, and that equals the performance of so-called Amazon Turk workers. So Amazon Turk workers are ordinary people who spend some of their free time by answering questions in some studies. And they had given them the data of 50 real defendants, and they had to estimate whether this person, based on the information they have, will commit another crime or not. And you can imagine they got $1 for 50 judgments, how careful they worked. And they were as good as the Compass algorithm. That's about the quality. And the Compass algorithm had also prejudices to boot. So I give these examples in order to make you critical and always ask for evidence. How good is these things that are being used? And the first distinction I want to make is between risk and uncertainty. So in the previous lecture, we mainly talked about risk. So this is where we have good statistics, or more or less good statistics, and we basically know everything that's coming. So if you play the lottery or if you go in a casino this evening, play the roulette, you know everything that can happen. So there are 36 numbers. There's the green numbers. Nothing else can happen. You know the probabilities, you know the outcomes. That's a situation of risk. And here, optimization and fine-tuning methods and complex methods and big data are likely to work if you have a stable world. But most situations are not like that. Certainly not in health. Certainly not in investment. And also in personal life. There are often things happening that you didn't expect. And if you try to find the ideal partner for the rest of your life, there will be surprises. That's all uncertainty. And here you need more than calculation and data. That's called heuristics, which bet on robustness. Before I go into this, let me say something about risk, which I have been asked to comment on. You may remember the celebrity case of Angelina Jolie, and where she was diagnosed having a mutation on the breast cancer gene, BRCA1, and she had asked her doctors what's the probability is that she may get breast cancer. And the number she reported is 87%. So before I go on, I was very much impressed about her doing this in this kind of reasoned way. That's not the point. So 87%, and she decided to do a double mastectomy. So I was curious, where do this 87% come from? And what do they mean? Again, percent of what? So the newspaper reported her doctor had told her that, or her doctors. Now, where do these doctors have fun? I could not get hold of any of numbers. I don't know whether someone of you has tried to find it. But finally, I thought maybe look up in Myriad. Myriad is the company who sells the tests. And wow, there was it on the website of Myriad. There was the number 87%. And also a reference. So I looked up the reference. And amazingly, this was a paper from a long time ago. I think it was 94 or 92. The reference, where there were no tests for breast cancer thing and so on. So I got this paper and read this paper. It was quite unreadable paper, like many medical papers. I often think they are read in a way so that you cannot understand it, even you try. Huh? But one was clear, the figure 87% was in the paper, right? But it was not about the probability that you get breast cancer if you have that genetic mutation. It was about something totally different. It was about the chance that a woman who has already breast cancer on one breast will get it on the other breast. There was nothing genetic in that. So that number was sold as the number as evidence for her. The story is one that you should never trust these numbers reported because there are always interested parties involved, like Myriad, who made a name out of this case. And you might just check these numbers where they are. And often, if you read the original study, you will discover, oh, it's something totally different. Huh? Isn't that interesting? So that was this story. But now we will, from now on, talk about uncertainty and about tools to solve uncertainty. And I'll basically give you a kind of basic course in heuristics. And it's no longer Kahneman's heuristics, which are all undefined and unclear. System 1 or System 2, nobody knows what it means. It explains everything after the fact, cannot predict anything. So these heuristics are precise, and you can actually test how good they are. I'll start with an example from sports. Anyone here who plays baseball? One? Okay. Cricket? One? Good, yeah. Soccer? Okay, what do you do all the time? Squash. Okay. Here's the situation. There's an outfielder, there's a fly ball, and an experienced player knows immediately where to run to catch the ball. How does he know that? How does he do it? There are two theories. One is it's a complex problem, so that it needs a complex solution. And what would be the complex solution? Though here I have a quote from Richard Dawkins in his wonderful book, The Selfish Gene, but that is the thing he got wrong. He says, when a man throws a ball high in the air and catches it again, he behaves as if he had solved a set of differential equations in predicting the trajectory of the ball. Okay? And at some subconscious level, something functionally equivalent to the mathematical calculus is going on. Something, so he doesn't know what it is. And note he puts in the as if. That's economist terminology. We don't care about how you make decisions. You always make decisions as if you would maximize some utility or so. That's the thing. So, okay. Differential equations. Have you ever calculated the trajectory of a ball? Here is it how it works. And the problem is not the calculation, the problem is the estimation of all of these numbers. For instance, alpha is the original angle where the ball was shot or thrown. And I also gave you here a simplified version because it has no wind, no spin. It's just a simple one. So that's the one vision. So players somehow unconsciously calculate that thing and estimate the thing. What else could they do? That's the thing. Now, the alternative is to study real players, what they do, rather than making up formulas. And a number of studies show that experienced players use a set of simple heuristics. And I'll show you the one which is probably the simplest of those. It's called the gaze heuristic. It has 3 steps. So it works if the ball is already high up in the air. Fix your gaze on the ball, start running, and then adjust your running speed so that the angle of gaze remains constant. So this player is now doing that. Watch, He's running in a way that the angle of gaze is always constant. See that? And what happens then is exactly where the ball is coming down. Do you want to see it again? The important thing is this player can ignore all the information in the equation and also the information that I left out, and focus on just one reason, which is the angle of gaze, and the problem is being solved. This is a heuristic, and it is an extreme heuristic, just looks at one thing and ignores all the rest. Got the idea? Do you have a dog at home? Yeah, more dogs than players. If you throw a frisbee, your dog, you will notice that your dog is not trying to calculate the trajectory, but he's running in a way to keep the optical angle constant. And if he succeeds on that, he will catch the frisbee. And in our research, we analyze how experts make intuitive decisions. And intuitive decision here is defined in the way, if you interview players, then most of them cannot tell you how you do it. They don't know about the gaze heuristic, but they practice it. That's called intuition. You can do something, but you cannot describe it. It's not in language. And many forms of expertise work this way. And also many forms of that, for instance, at some point in my life, I learned how to tie a tie. And it goes totally automatic, that is intuitive. I cannot describe it. And those men here who have a tie make the experiment afterwards when they go in the bathroom, untie it and tie it again. And while you tie it, you tell yourself what to do next. I tried it on myself. I couldn't get it done for 10 minutes. So that's also a way how you can disturb intuition, because it's not in language, not in consciousness, but you can do it nevertheless. So part of the program here is to work out the heuristics of experts that they use, and they're sometimes intuitive, sometimes they also know it, and then teach them to novices so that they can more quickly learn something. And that's also happening in many medical practices, where you learn by looking, or where you are actually taught a number of rules, like the Hinz rules. So we use in our research those heuristics that we analyze, and then we teach them as instructions how to handle situations of danger or of uncertainty, or in sports. Here's an example. You may remember the miracle on the Hudson River. A plane started from LaGuardia Airport, and after a few minutes something totally unexpected happened. A flock of Canadian geese collided with the plane. The jet turbines of modern planes are designed in a way so that they can digest birds, but not Canadian geese. They're too fat. And what happened is that both jets, both turbines, they shut down, and it got silent in the plane. We know from the passenger reports that they noticed something is wrong, suddenly silent. And we also know that there was no panic, but there was prayer. And the two pilots, Sullenberger and Scals, immediately turned around and had to make a decision about life and death. So, do we make it back to an airport, or do we have to take a real big risk, going into the Hudson River? How did they make that decision? So one could think that they calculated the trajectory, was the sailing trajectory, and see whether they make it. No. They used the same heuristic as the baseball player. In that case, it works this way. You fixate the tower of the airport through the cockpit windshield, and if the tower is going up in your windshield, you're not making it. You hit in before. And that is as safe and certain as anything can be. And that's the way Skiles reports that they made this decision. And if you have seen the film Sully, then you may remember that one tried to accuse Sully of having made a wrong decision because some algorithm calculated that it would have made it to the airport, and only later it was found out that the algorithm was calculating on wrong assumptions. So just imagine if they wouldn't have used this heuristic but trusted some algorithm, then it would be all dead. And the miracle helped that at the end everyone survived. So here's an example that a heuristic can always be used consciously or unconsciously. You can work it out, you can train people. And that's very different from if you read the heuristics and biases message that there might be two systems and one is heuristics are always unconscious, makes no sense at all. They are equally, you can always work them out consciously. Another application of the same kind is to interview and to work with experienced leaders in companies and to work out the heuristics they are using in order to deal with people and also with strategy. So an experienced leader has what I call an adaptive toolbox of rules, and if the person is good, he knows what rule to use in which situation. I'll give you a few examples from our research with Florida International University, the leadership department. And what you see are a few examples of heuristics that CEOs among the top 500 American companies use in order to deal with people and strategy. They're all very simple rules. The first one is hire well and let them do their job. So such a rule implements a climate of hire well, quality, and the second time let them do the job of trust in a company. And so, for instance, I'm at the Max Planck Institute, and the Max Planck works different from universities, that they have exactly this rule for the directors. So hire well takes a long time, an international search to find a good person, and then there's total trust. So as a director, one has all the money and all the personnel to do research. There's no need to write grants and short-term grants. Very different from universities. So there's trust. And that enables risk-taking. If I was a professor at the University of Chicago before, which I love, it's my favorite university in the world, but it's still, you have to write grants, and every 3 or 4 years, and who evaluates the grants? The average colleague. That's good to cut out the bad stuff, but it also has the problem that it cuts out innovation. And Max Planck has got the terms. So the director has all the things. I can hire whom I want and have a real interdisciplinary group working together. I can set the environment. And of course, it doesn't work all the time, this rule, but it enables innovation. Or second example, first listen, then speak. That's a rule for the superior, not for the person down. And there is a famous case of a Korean air crash where, to make it short, the captain had the wrong idea in this difficult situation. The co-pilot and the crew had the right idea, but the captain spoke. And Korea is a highly hierarchical society. And if the captain would have followed that rule and first listened what the others say, then the accident might have not happened. We do not know. Here are a few other examples. I go just in the last one under strategy. The rule is don't buy financial products you don't understand. If everyone on both sides of the Atlantic before the last crisis would have followed this rule, the crisis would not have happened as it did. So nobody would have bought these toxic papers, which many people bought because they thought the others understand what's being done, who also buy it, and so you have these things. So I recently met an executive of a large company, and she told me that many years ago, when someone proposed a business and her colleague executives nodded, she also nodded, not because she understood what's going on, but she didn't dare. And now she said, I've learned that, my lesson, after some things going wrong. And from now on, I always ask everyone, look, you have 15 minutes to explain your project to me. If I don't understand it, I won't buy it. And that's a very reasonable rule. So, yeah?
One thing that may help this group a little bit, it's not on your list of heuristics, but it's a heuristic that I use, and endodontists will understand this problem. And the heuristic is, if a person doesn't perform well after you hire them within the first 90 or 120 days, don't sit there and live with them for 6 months. Get rid of them. It's a 90, 120 day period. If you don't know by then, let them go.
Yeah. Which is tough for me.
It's hard.
Want to delay this kind of.
It's hard, but they can make your life a living hell.
Right.
Yeah.
Understand that part, yeah.
So, yeah, it's a heuristic, yeah. It's a simple, it can go wrong, but it helps you usually, yeah. Also, what's important on that matter is the environment you set up. So in my research group, which is interdisciplinary, and the people are from 10 disciplines at any point of time, we have a number of rules. One is, there is coffee and tea every day at 4 o'clock. And it's not a waste of time. And it's organized by the researchers, not by the secretaries. They need to be involved in that thing. Yeah? And it has helped. It creates trust. People talk with one another. They dare to expose their own ignorance. And that's just an example. Another rule is all doors open. Another rule is I try to keep everyone on the same floor. So when the group grew, and the architects came and said, we build a new building in the premises. I said, no, we're not building a new building, and half of my people are over there and half there. We built on horizontally, and we did. So in order to keep everyone on the same floor, people behave as if they would still live in the savannah, looking for others straight on, back, left, right, but not up in the trees or underground. And if you have a research group and half of them 2 floors down, you're lost. You lose 50% of your innovation and interaction. That's the problem. So there are a number of useful rules to set up. We also have a retreat every year. We have our own castle. That's not in Bavaria where we're going to, but that's very important. So here's the research program on heuristic. That's the alternative to heuristics and biases. So the first question is descriptive. So what's in the adaptive toolbox of an executive, of an ordinary person, of people, of institutions? And there are sub-questions. What are the heuristics? What's their building blocks? And what human capacities do they exploit? The second question is new. It's the question of ecological rationality, meaning when is a heuristic better than more complex methods, and when is this not the case? It's called ecological rationality because it's about the when you need to describe the situation. So for instance, big data doesn't work very well if surprising things happen. That's something like that. An intuitive design is then the consequence that you apply all of that to create decision systems that are simple and intuitive in the sense they mirror what people anyhow do, but highly effective. And I give you a few examples of that. That's the program. Adaptive toolbox. There are classes of heuristics, and I begin with the simplest one. It's like the gaze heuristic. You just look at one reason and ignore all the rest. According to standard heuristics and biases, this must be a bias. Why would people just look at one thing? Because they are intellectually somehow hampered or have cognitive limitations or that. Don't believe that. So you need to show whether it works. Here's a case about one reason decision making for a question, how to predict customer behavior. What does it mean? Assume you have a large company with a database of 100,000 of customers, and you want to send targeted information, could be catalogs, could be certain offers, but you don't want to waste your time and money with customers who will not buy again. So these are so-called inactive customers. You only want to target the active ones. How to predict whether a customer is inactive or active? That's a difficult question. And this is one under high uncertainty, because what motivates a customer to buy, it's infinite reasons of that. Again, how to do this, there are two philosophies, just like in the base building. One is, it's a complex problem, we need a complex algorithm. And here's the standard answer from marketing theory. I'm not going with you through the mathematics, I just want to impress you. Because if you don't understand it, you will be impressed. So, anyhow, a number of assumptions is made, there are a number of free parameters, and it delivers what you want, namely the probability that a customer will buy again. That's what it is. And it's just one example, the Pareto negative binomial distribution model. So the details are not important, but the thing is you try to make something very complex and come up with a probability. And so that's the world of complex solutions for complex problems. The alternative is to study what real experienced managers do. And two colleagues of mine, two professors of marketing, found out that real managers don't use these models that marketing theory proposes, but they use a simple heuristic. And all of them, this was 3 businesses, they use the same heuristic, which is called the hiatus heuristic. If a customer has not purchased within 9 months, classify as inactive, otherwise active. This is a heuristic, again, that goes with one good reason and ignores everything else. Ignores everything else means ignoring things that the Pareto model has, like the frequency of business or the spacing or whatever you can think about. And can always make an argument you should not ignore that because, but we will see in a minute, and I want to make it understandable to you, that under uncertainty you need to ignore to some part. So my 2 colleagues then set out and did something unusual, which is different from what many do. The usual answer is, we assume a priori that the complex model is better, and we look for an explanation, so we have a difference, we want to see this right, and what people do, and we blame the people instead of the model. That's the standard of the heuristics and biases model. And they didn't do that. They set out and tested it and found out which one predicts better. And they were convinced that the complex model predicts better because it has more information. So here's the result they got. Sorry. What you see here on the x-axis is the number of correct predictions. Up is better. These are 3 businesses where they had looked at that, and it's prediction, not data fitting. It's prediction. So if you only would look at the complex model, you would see, oh, it makes 74% correct here, 75 here, and even 75 there. Great, better than chance, significant. But if you test competitively, against a simple heuristic, you see, just looking at one reason is better than doing the complex model. And the same here, even strikingly better. And here it's the same. Here just you save all the effort doing your estimation and you get all the software part. So what you see here is the complex model, the Pareto model, has all the information the simple heuristic has, which has only one piece, and nevertheless does better in prediction. That's called a less is more effect. So by looking at a part of the information, you can do better than looking at all the information. That sounds very counterintuitive. And now the first thing is to understand, I started out with the distinction between situations of risk and uncertainty. If it's a situation of risk where you know the entire future and all the probabilities, no less is more effects will ever happen. Or in other words, if you have the data already, know everything, and then fit your model on that, you can't find a less is more effect. The more free parameters you have, the better the fit. But that doesn't hold for the prediction, because you overfit. And fitting is easy, prediction is hard. And so that was the first demonstration. And then I joined them, and we sat together and tested 24 of businesses, and also tested against other kinds of complex models, because then the argument is always wasn't the right complex model. It was always the right one until you show it's not if other. And here is something. Just look at the left one. These are now. Here we have now 24 businesses, and it's the average correct predictions. Here you have the Pareto model, as before, doesn't do too well. This is another model from the same class. It does even worse. But here we have two powerful competitors. That's logistic regression, a standard model in economics, which also looks at many more variables. And here we have basically one of the most powerful prediction algorithms in machine learning, random forests. I'm not going to explain these things. But what you see here is that just looking on one reason, on average, you make better predictions than all these complex things, which first, most people don't understand, and second, are expensive, and third, you spend lots of time with that, and they are not intuitive. Then we also tested other problems, all repeat problems, whether a patient will come again into the emergency room, or whether weather reports, whether the tornado will hit again in there. So that's the situation, or a sports team will win again. And you can see that even outside of this area, on average, relying on just one powerful reason outperforms the others. So then we got interested, when does this happen and when does it not happen? That's the real question. This is only an existence proof that the story about heuristics being always second best is plainly wrong. So here's one condition. I don't want to go too much in mathematics with you, but this one is very easy to understand. It basically says, so we have, say here, 5 predictors. And these are the weights. You can think of the weights as in a logistic regression or anyone else. And if the weights have a dominant Q structure, and the dominant Q structure is defined that the weight of the first variable is larger than the sum of what all the other variables in addition bring, then it's plainly clear that if you just rely on this one, whatever they say doesn't matter. And amazingly, we find this structure in many situations. There is one powerful Q, and the additional, what the others bring addition, is not really very much. And then is a kind of way to understand when just one good reason matters. So important is this methodological principle. You need formal models of heuristics, not vague levels, as system one or availability or representativeness. These have many meanings, and you can almost everything explain post hoc. Yeah? And you need competitive testing, not just test your own favorite model against a null. And also tests of prediction, not of data fitting. That's very important. If you think these methodological principles are followed all the time, no. It's rather the case that people don't follow them. And you don't get you have great R squares in data fitting, yeah, but not as great in prediction because it's harder. So here's another example about a class of heuristics called satisficing. So that was what Howard Simon proposed. Satisficing is in opposition to optimizing, and you can only optimize in a world which you know. Otherwise, so under risk, but not here. And I hit at this problem when my car, a BMW, I'm coming from Munich, so BMW is the method of choice, was 15 years old and needed a new one. And I was in the largest BMW dealership in Munich, and I had two cars which were basically identical, as identical they came, but priced very differently, something like that. So I asked the salesperson, why do they have different prices? With the same mileage, same age, same everything same as it can be. And is there something wrong? No, he said. That's the way we price it. And he explained to me how. So, do you have an idea why they can, why twins get different prices? Before I explain it to you. Sorry?
Because you'll think you get a good deal on that one. You'd want that one because you'd get a better deal. It just motivates people to buy that car.
That could be, yeah. So you price one just too high and the other one low, then buy the low one, yeah. But it's not the case. It is, so how they price is, so this is what the dealer explained me, and we checked it then. So he said, okay, we would just put in the average price from comparable, then we wait a month. If it's not sold, we go down. Wait another month, not sold, we go down, and so on until it's being sold. And the one with the cheaper one has been here for 2 months, and the other one has just got in. They're identical. Huh? But it's a matter, you see this, yeah? A matter of down pricing. So a salesman can tell you anything. Yeah? Yeah. So we checked that. And we checked that by looking at all the prices that are on the internet and followed them for over a year, how they developed and when they were sold. And we found that was over 600 dealers, over 16,000 cars, all BMWs, either 3 or 7. And almost every one of the dealers, something 99%, used aspiration level pricing. That's satisficing. And there are 3 basic ones. One is, the green one is those who start with a high price and keep it long, then go down. And those who start with a little bit lower one and make shorter, that's about the 4 weeks or so. And then a few who start with a lower price, the blue one, and never adjust it. So, which is also reasonable. If you start with a high price, never adjust it, you're stupid. You ever sit with your car. So, the point is that these satisficing is a heuristic that is used by almost every BMW dealer. And then the question is, how good is it? And we tested against the standard economic model. It made about twice as profit. Although the others are optimization model, and these are stupid dealers who don't know what to do, that's the prejudice of some social scientists. So here's the third example. And there are many situations where people do aspiration level setting. First, you sell a house, you ask a price, you keep it, and then say, now you have to lower down, and so on. Typical strategies. Economics theory tells you, no, you shouldn't do that. You should calculate the optimal point, but that's usually not possible. A third class of heuristic is equal division. Okay, that's the last example I show you, then they'll make a break. How to diversify? So assume you have a sum of money you want to invest it. And you don't want to put everything in the same basket, but you want to diversify over n options. But how? Now, Harry Markowitz from the University of Chicago got his economics Nobel Prize for finding the solution. The solution is called the mean variance model. Has anyone here studied finance or economics? If you would have all been brought up with that. It's like the mother milk of finance. And again, the problem is not the calculation. It's never the calculation here, but it's the estimation of all of these things. So you basically have to estimate for each of your n assets what the future return will be, and the variance of the future return, and also the covariance matrix on that. And that increases exponentially if you have more things. So, anyhow, but Nobel Prize gotten optimization model there. So when Harry Markowitz made his own investment for the time after his retirement, he used his Nobel Prize winning optimization method. So we might think, no, he did not. He used a simple heuristic that we call 1 over n, which means you divide your money equally. If n is 2 options, 50-50. It's 3, a third. It's easy. It's a heuristic because he ignores the information. Huh? See that? So the Markowitz model needs years of data in order to estimate its parameters. 1 over n needs 0 data. It's the opposite of big data. It's no data. So it bets on being robust. And so then the question is, how good is it? And for instance, a study showed they used 8 investment problems. So like one of them, 10 American industrial funds. And for Markowitz optimization, there were 10 years of stock data. And in order to estimate, 1 over n is already done. Yeah? It needs no data. What was the result? In 7 out of 8 of these cases, 1 over n made more profit than Markowitz optimization, according to standard measures like Sharpe ratio. So here's another less is more effect. The interesting question is, when does this happen and when does this not happen? And here is a kind of non-mathematical situation. Remember, we had risk versus uncertainty. Now we have a little bit more differentiated. We have low uncertainty, few alternatives, high amount of data. So few alternatives would be if the n is smaller. That's the world of complex solution. That's the world of Markowitz optimization. That's the world of big data. On the other hand, if you have high uncertainty and many alternatives and a small amount of data, then go simple. And that's the world of simple heuristics. And then you can do also a calculation. So for instance, in that study, the question was, how many years of stock data would we need so that Markowitz optimization finally gets as good as simple 1 over n? And for 50 options, the answer, the estimate was 500 years of stock data. That is in the year 2500. You can stop relying on simple heuristics and do the optimization model, provided the same stocks are still around and the stock market in the first place. So do our banks understand that difference between simple and uncertain and complex and certain world? I'll show you a letter that I got from my own internet bank. And I have to translate it for those who cannot read German, if there is anyone. It says, with Nobel Prize winning strategy to success in investment. That letter was sent to everyone. Huh? And then it read, do you know Harry Markowitz? No, but you should. And then they explained that this man won the Nobel Prize in economics with his mean variance model, and the bank is now doing the same thing. Yeah? And you should not trust your intuitions or simple rules, but optimization. What this bank has not understood is that I sent the letter 500 years too early. So that's where we make a break. And I think we continue when? After lunch. When is after lunch? 2:30, yeah? Thank you for your attention. Okay, now after lunch, where your stomach is still working, I will challenge you a little bit, and by trying to explain the general principles why heuristics work, and why, for instance, one good reason is can be better than everything else. So here's this. By the way, this is a quote by Herbert Simon, who is the father of what's called bounded rationality, and who wanted to implement a program to study how the mind and the environment work together. So that's his scissors metaphor. So you only understand how a pair of scissors cuts if you look at how the two blades fit together. Not about one blade, not about the other blade. And that's a metaphor. And ecological rationality is more the scientific study of this metaphor. So here's the standard account why people use heuristics. It's called the accuracy-effort trade-off. And that has been proposed by many people. And the idea is that a heuristic is simple, it saves effort, therefore you suffer or sacrifice accuracy. I just gave you some example that this is not correct. Technically, you can write that down and say the total error, say in prediction or in anything, is a bias and noise. So the biases, and then the idea is you should get rid of the bias and then you're perfect. That is only true in situations of risk where you know everything and nothing particular interesting is happening. Under uncertainty, this approach is incorrect, and you need a different approach, and it has one more component. It's called variance. And variance can be understood as the overly sensitivity of your model to specifics in the sample you had. And I explain that now without using any math by an analogy. So there are two dartboards. The player on the left side constantly throws too low and too far to the right. That person has a bias, and the bias is defined by the average position of the darts, so the crosses here, the distance between the average dart and the bullseye. That's the bias. That person also has another error. So it's called variance, the variability of the darts around the average position of the darts. So that's the variability here. See that? And they add together. On the right side, you have a player who has no bias, zero bias, because on average, the darts, on average, they are in the bullseye, but only on average. And this player has a large variance. That's the variability across the mean who happens to be in the bullseye. And that illustrates that it is not enough to try to reduce the bias, but you have two kinds of errors. In other words, the variance is often called overfitting. And we also know the factors. If you have small sample size, then you have probably large variance. If you have complicated models with many free parameters, you generate large variance. So let's connect that. Think about the one reason heuristic, like the hiatus heuristic with a fixed hiatus of 9 months, say. That heuristic doesn't estimate anything. So it's not dependent from sample, and it has a variance of 0. It has probably a large bias, and that's the dilemma. So if you have tried to reduce the bias, then you create, like on the right side, lots of variance.
Can I just ask a question, because I've been thinking about this? In the second trial, what if the accuracy is very similar to that, but they're in a different location? In other words, the first trial they're there, the second trial the bias is further away, but they're all together.
It means on the right is
On the left, I mean.
left is first.
Yeah, on the left. So your second trial, they're positioned like that, but they're in a completely different area. How does the formula account for that variance? Is that in the variance formula?
So the variance here is the deviation of all these here around the mean. Yeah. The variance here is the deviation of all these around their mean. So the variance is here much, much bigger. Well, Nancy Cartwright calls it precision. So this is a high precision here, and this is a low precision, but it's just another word for that. So the important thing to understand is that you have a kind of a dilemma. So if you use a simple heuristic that decreases the error due to variance. So if it has no free parameter, that means it doesn't use any data to learn, then the variance is 0. You always have to dart at the same position. And if you have a model with lots of free parameters, then you create more variability because you estimate the parameters from sample. So if you think in statistical terms, each of the darts is the mean of a sample. Okay? And if the sample size is small, then they're all over the place. If the sample size is large, then they're closer together. So that here illustrates the difference between bias and variance. It does not illustrate the dilemma. But the dilemma is that usually, if you try to reduce variability, by having a simple heuristic, you increase the bias, and vice versa. And it just turns out that in most of the time where one studies it, the complex models, so let's do Markowitz on that. Remember Markowitz, 1 over n. 1 over n, so start with Markowitz. Mean variance is a method that estimates its many, many parameters from a sample. If it would be a different sample, it would get different parameters. So that's basically, that's one set of parameters, that's another one, that's another one, that's another one, another one. And it is highly sensitive to the specific sample it got. So depending what kind of data you use in order to calibrate your mean variance, you get different things. Right? The 1 over n has no free parameter. It doesn't estimate anything. It always gets the same solution. It's not dependent on any data. So you might think about, it's like having a strong opinion And you don't ask any people and always change your opinion. That's the other side. It is now 1 over n has no error due to variance, so they're all in one point, but it may have a larger bias. But if the bias is not larger than the sum of the mean variance bias plus variance, then it does better. So that's the real question.
Wait, can you say the last part again?
Okay. Mean variance model has two kinds of error. It has a bias, it's not the truth, and it also creates lots of variance because it is dependent on the sample. 1 over n has no variance because it's insensitive to any samples. It doesn't use anything, but probably a higher bias. And then, so how can we now understand that the simple heuristic can outperform mean variance is if the bias of the simple heuristic is smaller than the sum of the bias and the variance of the complex method. Because the complex method has two sources of error. And it may or may not be, that's the question. And it's a result from other things. For instance, if you have large sample sizes, then, as in the example I gave you, 500 years of data, then the complex model tend to do better. Then tend to do better would mean that these wide variability would get slower.
But on that the example of the one on the left with the bias, you could have a high bias, you could have all that little group, low variance, they're all clumped together, but that whole thing could be further away from your target.
Right. Yeah. And that's the question, whether the bias, here it's simply the bias, what the heuristic does here, is smaller or larger than the sum of the bias and the variance, precisely the squared bias. So that's a way to understand this. And I will give you another example to work on, because what I'm trying to teach you is what most behavioral economists have still not understood. And what I'm trying to teach you is well known in machine learning, but the disciplines are so isolated that they do not learn very much from another. So how can one decrease variance? There's a question first.
I just want to be clear that for myself, maybe for the audience, variance is a squared term as well, isn't it?
Yeah, it is already a squared term. This is why the bias is a squared term. Right. Good question.
Why isn't it put up there as squared? How is it already squared?
Or I could write standard deviation squared. It's just not practice. But it's an important question. So here are a few ways how heuristics can reduce the error due to variance. That's what they're doing. Having equal weights, as in 1 over n, so you don't even estimate all these weights. And one reason heuristics, it ignores just all the other heuristics, or lexicographic heuristic. We'll see these an example in a minute. So these are some of the ways to simplify. Think about Einstein's quote, which was up here. Make everything as simple as you can, but not too simple. That's exactly the philosophy of bias and variance. You reduce the complexity to a degree where you actually reduce the error due to variance without losing too much out in terms of bias, but not too much. And that's exactly this bias variance dilemma. I'll give you another example, which may be helpful to understand that. So here you see the temperature in London in the year 2000. Every point is the average daily temperature. And as you can see, it goes up, even in London in the summer, and goes down. Now assume you would want to understand the temperature or model them. And you have, you're mathematically inclined and you think about polynomials. And a polynomial of first degree is a line. And that's not a good model for temperature in London. It may work on the equator, but not in London. A polynomial second degree is a parabola. It goes up and down. But it's also not a good model because next year it should go up again. So the third degree can already go up. And what is here is two polynomials being fitted. One of third degree, the green one, and one of 12th degree, the red one. 12th degree is immensely flexible relative to a 3 degree. So that's called data fitting. The data is already there. You fit your curves. Now, which one of the two curves, the red or green, fits better? Red, right. Yeah? And now, what polynomial of what degree would you need to have a perfect fit? So a polynomial of degree 364. Huh? See? And that also tells you that fitting is not a good measure of the quality of a model, because you have just more freedom of degrees and free parameters than you have data points, or exactly the same thing. So with a polynomial of 364th degree, you can draw the curves through every data point. But that's clearly overfitting and creates huge variance. So now we do the following. Now we predict with that two models here, we predict next year's temperature. Or equally, we can take a sample of 30 or so out of that and predict the entire thing. Now it's about prediction. So far we have no prediction. We do data fitting. Data fitting is like hindsight. Huh? You have your data, you fit it. So first, what you see here is the result of fitting now many models, not just the 3 and 12. And please ask questions, because that's important to put it into your mind. Huh? And it may not be easy. So this is error. So good is down, so little error, and up is bad. We had a polynomial of 3rd degree, that's the average error. We had a polynomial of 12th degree, has smaller error. And if we would go on here to 364, we would have 0 error. But again, this is pointless to make complex models that fit very well. We want to predict. And now is a question. If you take all these models, like the green and red one we've seen before, and now predict, say, next year's temperature, or we take a subsample and predict the entire of the other year, just prediction. How will the prediction results look like? So first question, now we do for every of these a prediction curve, not a fitting curve. Will the prediction curve be above the red curve or below the red curve? Above, right. And why? Yeah, because prediction is difficult, yeah, right. And if you're socially smart, then you noticed I left more place up. What happened? Well, it must be up. Okay. And then the next question is, will the curve also be something going down from here, and so that the more complex models will always have lower error? Or what's the shape of the prediction curve? You mean this? Any other proposals?
Straight line, 2.
Straight line after 2. So this and then so? U. Now we have, I think, exhausted all possibilities. Okay, and the person in the first row is right. It's U-shaped. And that's interesting. Huh? So first interesting is, in prediction, the more complex model that fit better are no longer the better who predicts. Prediction corresponds to risk. You know already. That's the case where the best model under risk is not the best one under uncertainty. And also, the model that has the greatest fit, you shouldn't be impressed by that, because it may not have a good prediction, because it overfits. There's too much variance. And so what you see here is, at the extreme, this is a line, a polynomial of first degree, a line. Totally wrong. But if you compare that, so totally wrong means it has a high bias, but it has low variance. There's not much to fit with that. But compare that with the formerly winning 12th degree, it's better to have a real bad model and not too many flexibility. This here has now a low bias, but lots of variance. So it corresponds to the dartboard on the right side you saw before. And you can see that this is kind of like Einstein's dictum, so make it simpler, but not too simple. That's what it is. So somewhere here, polynomial degree 3 or so, you get the best results. But that's a way to understand that you need to balance the complexity of the model, variance, so the variance with the bias. And it's also a way to understand more clearly why heuristics work. That is, that they have a low bias, and the sum of the low bias plus the variance is smaller than the sum of the variance and the bias of the complex models. That's the situation. This is a thinking model, because it's also based on certain statistical assumptions, but it's a way to help to understand things. And in the example of 1 over n, 1 over n is extreme because it's on the total other end. So there are situations under high uncertainty, and investment is high uncertainty, where you better get really simple. That doesn't always. You won't hear this from financial experts, this message, particularly not for those who sell their advice. Some time ago, I gave a keynote to Morningstar. Morningstar is one of these big investment firms on simple heuristics in finance, and was giving several examples, including that one here. Then there was a podium, and with two of the major investors, and the moderator asked one of them, said, Professor Gigerenz just showed that simple heuristic can do better than complex models. You are known for complex models. What do you say? So everyone was waiting, whose blood is being shed here? And to everyone's surprises, the man said, yeah, I have to admit I often do 1 over n. And the moderator said, you never had said that before. But you see, it is this man, I do not know, but my interpretation is he knows exactly that all this complexity is just hot air. But he also feels that he has to produce this hot air because it impresses people.
Gerd, isn't those no-load exchange-traded funds, aren't they based on 1 over n? Isn't that how they do it?
Yeah, there are funds. So an index fund is close to 1 over n. They still weighted, and that's always a good idea. If you have no idea about stocks, and if you do not want to pay someone who sells useless advice, then just buy the Dow Jones or some other big Standard & Poor 500, some index fund. And they are hard to beat by any expert. And you don't have to pay fees. Yeah. That's just a consequence there. Or just invest your own money. So after this Morningstar event, the head of AXA investment in Germany came up to me and said, okay, we'll check what he said. And he said, we will re-evaluate our investments since 1969. So AXA is a international insurance company. And they're always bought in these black box, complicated models and so on. And a few weeks later, he flew to Berlin and came to my office with his IT person who had done the calculations and said, Professor Gigerenzer, we convinced ourselves. Yeah? We checked it, and independent of the rebalancing method, 1 over n always made more profit than what we used. So we are convinced, but, he said, here is our problem. How do we explain this to our customers? They might say, I can do that. See the problem. And and AXA still has no, simple heuristics fund. This person wanted to set up one, but then at some point he decided he doesn't want to make more money, he wants more freedom, and just traveled around the world and sent me emails from everywhere. But the fund never realized. Yeah, okay. So there are a number of studies about financial advisors. You should look that up. For instance, one study, a wonderful study, it's extreme, was in Sweden, and they had given financial advisors, the professionals, pairs of stocks. And the only question was, which one of these will make more money tomorrow? That's easy. Huh? You have a 50% chance. With lots of these. Yeah? And as a control, they had ordinary people. Now, the ordinary people got 50% right, as you can, on average. The Swedish professionals got 40% right. You know. Yes, and then, of course, the authors of the study didn't believe that. They replicated that with other professionals. They also got 40% right. So, it's another thing that I think it's a good chance to realize, think yourself in these situations. So, let's move on to intuitive design. Intuitive design is the use of the scientific results in the study of the adaptive toolbox. So what kind of heuristics do people use? How do they think? Combine that with the study of the ecological rationality. In what situation does that work? And it's basically the design of expert systems that do have an intuitive property and not these expert systems that nobody understands. That's the idea. At the same time, not losing predictive accuracy. See that? I give you, the first example is from healthcare. So a man is rushed into a hospital with severe chest pains. The doctors have to make a decision about life and death. Should we send him into the coronary care unit or in a regular bed with telemetry? So if the person gets a cardiac event, should be in the care unit. If not, better in the regular bed. In one hospital in Michigan, doctors sent 90% of all patients in this situation in the coronary care unit, although only 15% on average had a heart attack or a cardiac event. That's called defensive decision making. Because if the patient is in the regular bed and gets a heart attack, the doctor may be sued. If the patient is sent in the coronary care unit, and like one of my colleagues, got an infection there that he wouldn't have gotten elsewhere and dies from it, that's okay, because you did everything. So that's the situation. But the problem was that the costs increased, the coronary care unit was overcrowded, the quality went down, and they asked a team from the University of Michigan, a team of medical researchers, to help them. And the medical researchers had, their first idea was complex problems, we need a complex solution for that. Here is the complex solution. So they gave the doctors a chart with about 50 probabilities, here in percentages. You don't need to understand the variables. The doctors understand the variables, but they don't understand why there's 19% or 35%. And then they got a pocket calculator in which a logistic regression was implemented, and they pushed in for each patient the numbers, and then pushed enter, and then a number appeared, and if it was above a threshold, coronary care unit, otherwise regular bed. That's a typical decision problem. This decision system proved later better than doctors' defensive decision making, but it also became clear that the moment the researchers left the hospital, the chart and the pocket calculator were put aside and doctors went back to defensive decision making. They don't like to use something they don't understand. At this point, the PI of the University of Michigan team learned about our research on fast and frugal heuristics and used a template of a heuristic in order to create a heuristic system for the prediction of cardiac events, or in other words, for allocation to either coronary care unit or regular bed. Here it is. So what you see here, it is a so-called fast and frugal decision tree. A fast and frugal decision tree is not a complete decision tree, but it has an exit that is a decision at every question. It asks only 3 questions. So first, is there an anomaly in the ST segment, so in the electrocardiogram? If yes, immediately coronary care unit. No other question is asked. If no, a second question is asked, whether the chief complaints are chest pain. If no, regular bed, no other question is asked. Otherwise, the question is one of these factors, the heuristic is present and it decides everything. So this is fast and frugal because you may only need one variable and not more. And also, it is intuitive in understanding because it mirrors doctors and people's decision in general. You do it sequentially. You look at one thing that may decide it. If not, you look at something else. But it does it in a systematic way. And it's also transparent. So that also means that that system is by now used for many years and also adopted. So if there is a different patient population, you may change or switch these variables or add others, and which is very hard with a logistic regression system which you don't understand. But then the question is, okay, that is faster, it uses less information, it is transparent, but how good is it? And I'll show you now the study that was done at the Michigan hospital. Will be a so-called ROC plot. You have here the sensitivity, that is the proportion of patients who are correctly assigned into the coronary care unit. And correctly assigned proportion should be high. Yes. Here is the false positive rate. That means the proportion of patients incorrectly sent into the care unit. That should be low. And the ideal system should be up here. But there is nothing up here that we know. It's too complicated and too difficult. That's the line of chains. So if you send nobody in the coronary carrion, you're there. If you send everyone, you're there. Huh? If you throw dice, you're somewhere in between. There is an area where you do not want to be. That's this area. Because you do less than chance. So, I'll show you now the results of this study done. And there will be 3 results. How well did physicians defensive decision making? Second, the complex model, the heart disease predictive instrument, and the simple heuristic. So where do you think are the physicians? Remember, they sent 90% of all people into the coronary care unit. So it must be a number that is rather up here in this area. Because otherwise they would send, if they would send almost nobody in there. But where do you think is the number? Above chains, at chains, below chains. Below chains, these are your colleagues, aren't they? And you're right, slightly below chains. So they send about 90% of those who should be in, but also slightly more of those who should not be in. That's defensive decision. It protects them. The next thing is this complex system where you saw the chart with some 50 probabilities. Now, these systems give you not just 1 point, but many points, because you can just adopt this threshold. But they should be on the right side of the red line. And you see they are on the right side, and they get a little bit weak up there. So that's called an ROC curve. And so if the curve would be like here, that would be not as good. And the curve, if the points would be out here, that would be better. Okay. Now, where do you think the simple heuristic that you just saw ended up in this quality control? It's 1 point now. So it has a sensitivity that is higher than all of those and has a false alarm rate in the 50s. So it's outside of the ROC curve, that is, it outperforms the ROC curve. And so that's another illustration of a less is more effect. And here we have a situation which is not out of sample as in the exercises that I showed before, but out of population. So it's a typical situation in medicine. So this system was validated in Boston, now it's used in Michigan, and nobody knows how the population is different. Huh? And the point is to use it there, not to test it again, develop one. Huh? And this is why here the more goes, so cut it down, make it simpler. And that's the goal here. I'll show you now a second tree that is part of my work with the Bank of England. So that's part of the work on simple heuristics for a safer world of finance. Maybe I should say a word to that. Part of the problem of the last financial crisis were the mathematical models. These models are made, like Markowitz model, for a world of risk, where you assume the world is stable, you know everything. But they're used in a world of uncertainty, the world of finance. And the regulations, so the Bank of England is the regulatory body in Great Britain, and the regulations that exist, they're called Basel I, Basel II, Basel III. They got ever more complicated. So Basel I was 30 pages, Basel III over 300 pages, Basel II over 300 pages, Basel III over 600 pages. So the idea is, if something doesn't work, make it more complex. While the alternative would be, if something doesn't work, make it simpler. But that doesn't occur to these economists. The Bank of England is the only bank who has now this insight. And just to illustrate to you the amount of error due to variance that comes in is, so is any one of you, does any one of you have a big bank, owns one, or no? Okay, just assume. So if you take a large bank, these banks need, according to Basel II and III, calculate their value at risk. So a value at risk determines the amount of money you have to have, your own capital, in order to, say, only get bust once in 1,000 years. That's a typical value at risk. In order to, they have prevented no crisis so far. Just make it clear. In order to calculate this value at risk, a large bank has to estimate thousands of risk factors. They're all in the future. And since the risk factors correlate, they have to estimate a correlation matrix in the order of millions. Good luck. That borders on astrology, what they're doing. And I have never had anyone contradicting this statement which I just made. Recently, I gave a talk to the European Central Bank. They were just nodding. Yeah, but that's what we have to do. That's the kind of, that's how it is. Yeah? So that doesn't create certainty. And the question is, can we make it simpler in order to make the world of banking safer? And here's a fast and frugal tree that we are testing for the way, so I'm not going into the details here, but you can see it only asks only 3 questions. Whether certain things like leverages are there, whether they're not there, and then it's either a red flag or no red flag. So these are examples about how to design fast and frugal tree. And for instance, today when I started out with the Ottawa-Enkel rules, that's also a fast and frugal tree. So a simple tree that has an exit everywhere. So let's move on in our travel through the world of risk and uncertainty. And go back to the distinction between risk and uncertainty. We live in a society where people like to pretend that the problem would be all of risk, that you can calculate everything, and not of uncertainty. The confusions of uncertainty with risk is called the turkey illusion. Why turkey illusion? Assume you are a turkey. It is the first day of your life. A man comes in and you fear he will kill me, but he feeds you. On the second day of your life, the man comes again. You fear he will kill me. No, he feeds you. On the third day of your life, the same thing. According to Bayesian probability updating, the probability that he will feed you and not kill you goes up every day a bit. On day 100, it is higher up than ever before, but it's the day before Thanksgiving and your dead meat. So the turkey was not in a world where he knew all the risks and everything that could happen. The turkey illusion is probably more often committed by people and not by turkeys. And I give you here an example from that area. So Robert Lucas, one of the best-known macroeconomists, said in 2003, 4 years before the financial crisis hit, that we are safe. The central problem of depression prevention has been solved for all practical purposes and has in fact been solved for many decades. 4 years later, the greatest depression since the Great Depression hit. So that's a turkey illusion. And why is this a turkey illusion? It's the same thing if you look at the predictions of the banks or of the rating agencies. The the predictions went up and up and up, and the prediction volatility went down and down and down just before the crisis hit. And why? Because these, for instance, the rating agencies like Standard & Poor, they use data to calibrate their model. They typically last 5 years. And then all they can predict is it will go up. Yeah? Because that's in the data. And that was actually the case. And that's the same situation as the turkey. It was fed every day. Yeah.
Why couldn't they estimate the value at risk with all these derivatives? It wouldn't seem to me to be that difficult a job to at least estimate that risk.
Yeah. They did estimate, it was just plainly wrong. And so the short answer is, so these are all models which are based on standard probability theory. And standard probability assumes a stable world. Otherwise it doesn't work. That's why it works with risk. And these models, they are right for many years. But when something unexpected happens, they fall down. So Nassim Taleb has written about that and showed very nicely that the predictions of these standard models, they predict right for 10 years and then goes down. Yeah? And the real losses occur here. They assume stabilities which don't exist. And he calls it a black swan, but whatever you call that, the very point is that these models don't work. They only work as long as nothing happens.
I don't know, it seems to me like a very unsophisticated system. It shouldn't be that hard to have a model that says, well, what if this bank fails? What if Lehman fails? Then what happens if this happens? How difficult could that be?
They do have this type of models, and they are highly sophisticated, and they're really proud about that. And that's the problem. I show you now a turkey illusion from the area of finance. And I hope you enjoy this. At the end of every year, the big financial institutions of the world make predictions for the exchange rate dollar-euro at the end of the following year. These predictions are bought by companies who do, say, overseas trading, and sometimes for lots of money, and what's expensive must be good, isn't it? I have not found a single study that was longer than a single year, where you can prove everything, about how good these predictions actually are. So I managed to get the data for 10 years of the top financial institutions. That's the list of institutions in the data set where I got the predictions from. Everyone is in this list who is famous or now infamous. So Bank of America, Merrill Lynch, Barclays, Deutsche Bank, Credit Suisse, and Morgan Stanley, JP Morgan, and so on. So every of these financial institutions makes a prediction at the end of the year for the exchange rate the following year. Good? So here is the analysis. What you see here is the 12 months forecasts. The exchange rate, 1.0 means $1, €1. Higher means that the euro is stronger, and lower means that the dollar is stronger. Okay? So, each of these points is a prediction of these 22 financial institutions. We don't see 22 points because they overlap in part. The circle is the average prediction. That means at the end of 2000, the average prediction for the end of 2001 was about $1, €1. See that? there is considerable variability, which is not trivial. It's in the order of more than 20 cents. Clear? Good. So, what was the true exchange rates at the end of 2001? That's the true one. It was lower than all prediction except one. This is Citibank, now Citigroup. And I can tell you that was the last time in the 10 years they had luck. Imagine that you are a high-paid financial specialist and in charge of the predictions. It is now end of 2001. You make the predictions for the end of 2002. You were too high. What do? Are you going up or down? Up. Okay, you're going up. So that's what you're going down, yeah? Right. That's what they do. What did the exchange rate do? Went up. Note that the true value is outside of the entire spectrum of predictions. That's also not trivial because it's a broad spectrum. While in the last time, at least one was. Yeah. So now it's end of 2002. You're in charge of making the prediction, and you're a high-paid person. You were too low. What do? You go up. Now that's what they do. You might consider changing your profession. Where does the actual value go? Up. So the second time outside of the entire prediction spectrum. Now it's the end of 2003. You make predictions. What do? Up or down? Up. Yeah, you all go up. They do too. What does the real exchange rate do? It's still outside of the range of prediction. Now it's 2004. You make the prediction for 2005. What do? You get up. That's what they do. What does the exchange rate? Goes down. Now look at that. So 1, 2, 3, 4 times outside of the entire spectrum of things. That's an achievement. And also, we can now make a hypothesis about how they make the predictions. We do not know, because it's secret, because they're so good and expensive. But you see, one thing is that they basically do what you did. They predict the change of last year. And that means they're always with the predictions 1 year too late. So if you shift this curve, the prediction curve, down 1 year, you're fairly right. Now, with that knowledge about how this prediction or hypothesis is being made, we can now predict what they do now. It is 2005, 2006. What are the predictions? They're going down. Yes, they do. What does the true exchange rate? Goes up, but at least now in the range. That's the first time. In the range. And now the predictions are, they go up. Now we understand that, yes, slightly up. What does the true value is again outside of the entire range. So they go up further, the value goes down, and that's a hit. And it's the first and the last one. So now they go down because it went down, but it goes up, and they go up and it goes down. So you might ask yourself, why are these predictions made every year? And more, why do people buy these predictions? And there are two answers. One is those who buy don't know how bad they are. And there's some reason for that, because you have never seen this before. And the banks, they don't even calculate that. Because they intuitively know that there's nothing in it. But there's a much more interesting explanation. The managers probably feel very well that there is not much in this prediction, but they want to buy them nevertheless. And why? It's defensive decision making. So if you, as an executive of UBS, make your own prediction and it's wrong, it's your responsibility. But if you hire Morgan Stanley and they make another series of totally worthless predictions, it's okay, because it's their responsibility. So you waste your own money, or not your own money, the money of your own company, just to protect yourself. And also, you generate a series of young people who are mostly sophisticated, mathematically sophisticated, and their life is to make useless predictions and fine-tune the thing and so on. So that's the cause of defensive decision-making. That's an entire culture in which we live. And many products that we produce, its major value is to protect ourselves. So, here are 3 misconceptions. It's a summary of what I've said before. You find this misconception in almost every textbook still today. Heuristics produce second-best results. Optimization is always better. That is only true in a world of risk, not under uncertainty. Complex problems would need complex solutions. You've seen several examples. No, it's not true. And more information, more time, and more computation is always better. No. I have given you examples about more information, more computation, not about time. Okay, here's an example from sports. Who of you is playing, what do we choose? Golf. 1, 2, 3. Okay. You work all the time. Huh? Yeah. Or play squash. Okay. Assume the following situation. There are beginners in golf and experts. Both groups are instructed that they have to make their putt in 3 seconds. So the putt is there. Yeah, putt is put. And so that's possible, but it's not much time. What happens to the beginners if they have only 3 seconds to make their putt? Do they get better or worse? Who thinks better? Who thinks worse? Don't let yourself be impressed if someone shouts in better. So the beginners, if they have only 3 second time, they get worse. Now, beginners need time. It's like piano playing. You need to learn a way to put your fingers, and music only starts when you don't know anymore what's going on. The more interesting question is what happens to the experts. When they only have 3 seconds, do the experts get better or worse? Who thinks better? Who thinks worse? No. So the experts, they get better if they have only 3 seconds. And why is that? So expertise is intuition. And intuition is more or less automatical. And if you have too long time, you start thinking. And that's not good for intuition. By the way, have you noticed that after I asked the first time, well, those of you who dared to raise their hands got it wrong? The second time, there were fewer hands up. That's defensive decision making. Yeah? That's a negative error culture. You should raise your hands to make errors in order to learn. Okay. we have to do it again, this experiment. Now we have beginners and experts in golf. We instruct both groups that they should pay attention to the bodily movements, so to the execution of the hit. So what happens to beginners if they are instructed to pay exactly intuition to what they're doing? Do they get better or worse? Who thinks better? And who thinks worse? Yeah. The beginners get better if they are instructed to pay attention. You can measure this on average. And for the same reasons before. But the interesting question is what happens to experts if they're instructed to pay attention to the execution of their putt. Do the experts get better? Who thinks better? Who thinks worse? Now you got it. Good. And now you can use this in a pragmatic way. So if you would play tennis and your partner has a forehand today which you cannot handle, now you know what to do. When you change sides, you look at him and say, you have this marvelous forehand today. How do you do it? And you have a good chance that he starts thinking about it and the problem is solved. There's actually a famous situation in the Soccer World Championship in 2006, where Germany played Argentina, and it was a draw, and it got into penalty shoot. And penalty shoot is where the emotions of everyone. There are people there who cannot even look at it because it is. And it was a very unusual shooting, and it was everything. Who lost had to go home. And so the German goalie, Jens Lehmann, had a sheet of paper in his hand. Every time an Argentinian went to the point and was beginning to shoot. So assume you are an Argentinian player. And you know there are 75,000 people in Berlin. It was in Berlin. They are all. It's loud, it's incredibly. And you know, if you miss, it's the end. Yeah? And you're lynched at home in Argentina. Are there Argentinians here? So, and then the goalie has this sheet of paper, and you think, what's on it? And you correctly infer information about me, where I shoot, yeah? Right, left, up, down. And then you think, what do I do now? And Jens Lehmann held 2 of the penalty shoots, and Germany went on. Now, some of the referees I've talked to, they think it was because of the information on the sheet. The studies that we have show exactly it was something else, a psychological factor. You made the person think about what he's doing. And a soccer player is best when he doesn't think, if he can think. And that's also proven by the last decisive shot. This was an Argentinian player, and you can still see this in YouTube. You will see Jens Lehmann standing in the goal and studying that sheet of paper intensively. We have the sheet of paper. There's no information about the last player on it. That rules out the hypothesis that it was the information. It's a psychological factor. And more time is not always better. And particularly if it's about intuitions, then you can disturb them. So, okay. Let me, we are nearing slowly the end of this tour. And I would like to give you a little bit of information on a related issue on intuition and gut feelings. So intuition can be defined as the result of year-long of expertise where you know what to do, but you cannot explain it. It nevertheless guides lots of our professional and private life. As you know, intuition has gotten a bad name in the last years, totally ignoring that, for instance, Einstein said that the intuition is a secret gift, a sacred gift. And people have, and ratio is its servant, and people have made the servant to the, just confused the two. He was always arguing that his great ideas were all based on intuition, and then he had to work it out. So, intuition is not a sixth sense, it is not arbitrary, it is also not something given from God, and it's also not something that only women have, we men also have intuitions. But our society has problems with intuition. So in many situations it's suspicious because you cannot explain it. That's the thing. And we live more and more in societies where performance doesn't count anymore, but the procedure counts. And that's the problem. Even if an intuition is good, you can't explain it. And that's why it's considered dangerous. So let me ask you, how often is a decision in the big corporations internationally at the end a gut decision, so an intuitive decision? And I emphasize on the end because you usually, the executives will try to collect as much data, but sometimes in many situations the data doesn't tell you what to do. And then, if then you use your own experience and feel you should not do this and should these, and act on that, that's a gut decision, an intuitive decision. Clear? So it doesn't exclude thinking. And it's just basically the end of all of that when facts and data don't help anymore. I have worked with a number of large corporations, and I give you one example which is typical. This is from a leading international technology services provider. And I've asked the executives, from the managers until the executive board, how often do you rely on gut feelings in decision making? So exactly how often is an important decision that you made or where you participated at the end an intuitive decision? What do you think? How often does this happen? 0%? 1%? 2? 5? 50? I mean, 50 is always a good guess. That's called a heuristic. Here's the answer. You're totally right. So, this is the hierarchy in this company. There is nobody who said never an intuitive decision. There's also nobody who said always, and both is reasonable. On average, through the entire hierarchy, so every other decision is at the end a gut decision. And these are big decisions, whether they want to go to South Korea as opposed to Japan. The same executives would never admit that in public because of fear. If you make a gut decision and admit it, you take the responsibility. And we live in a society where there are fewer and fewer leaders who are willing to take responsibility. And I've observed two methods to deal with the anxiety about intuitive decisions and also responsibility. The first one is to find reasons after the fact. So one would, for instance, select an employee who is smart, and give him 2 weeks' time to find the reasons of a decision already made. And then the executive will present the decision to the world as a fact-based decision. The term intuition will never be mentioned. This is a waste of time, money, and intelligence only because one fears. One has to take over responsibility and also of consequences if something goes wrong. There is a variant of that which is more expensive. So the company, the leadership hires a consulting firm which then presents a 200-page document which gives the reasons for the decision already being made. That's an even greater waste of intelligence, because these consulting firms usually have very smart young people, and they have to do something which is finding reasons after the fact. I gave in the last years a few talks to one of the world's largest consulting firms and used a lunch with the principal to ask him whether he would be willing to tell me how many of his customer contacts involve providing reasons after the fact for already made decisions. He said, Dr. Gigerenzer, if you don't mention my name, I tell you, it's over 50%. That leaves room. Just imagine, it's a total waste. And the reasons are psychological and institutional, because there is a lack of error culture. So that's the first way, finding reasons after the fact. There's a second way, which is even more expensive to the companies. It's called defensive decision making. So a defensive decision means that an executive feels or thinks that option A would be the best for the company, but also knows if something goes wrong, it's my responsibility. If it's a gut feeling, by definition, I cannot explain it, looks very bad. Therefore, I'm not even mentioning this, and I recommend a second-class option where if things go wrong, I'm not in responsibility. That's called defensive decision-making. You protect yourself and you hurt your own company. How often do you think in these international technology services provider, decisions are made defensive? 90%. That's a tough bet. Huh? Anyone more? So I'll show you that's their own statements now about that. We have a little technical problem, but I think we can read. Consider 10 important decisions. That was the question. So important professional decisions. How many had a defensive component? And that's the same group of people. What you see now, the distribution is much flatter. So there are individual differences, strong. On the one side, there are people who say, I do this never. And if you interview them, then you get responses like, if the company is in good shape, I feel fine. If it's not in good shape, then I'm not in good shape. So here, the identification of the leader with the goals of the company functions. On the other extreme, you see a few who basically say, almost always. So 7 to 9 times out of 10. If you talk with them, they tell you, in this company, you must not make an error. You will be punished immediately. Or one said, we have no error culture. We don't even talk about errors. Another one said, my motto is cover your ass. So you get the impression. And these are mainly from the lower levels of the hierarchy. On average, across all the levels, every second or every third decision is defensive, according to their own account. And it's probably an underestimate, because not everyone admits it, and also not in front of him or herself. So defensive decision-making is not just a problem in big corporations, it's also a problem in medicine. So if you visit your doctor and believe that the doctor tells you, recommends you the best for you, you may be lucky. Gesundheit. You have a nice doctor. But many doctors practice defensive medicine. And I don't know how it is in your group, but the studies in the US show that study after study, more than 90% of physicians say that they practice defensive medicine, typically prescribing too much, too many antibiotics, too much medicine, unnecessary cancer screening, surgery, and so on. And the problem is in part the tort law, and you also have too many lawyers. That's another problem. The world would be better with fewer lawyers. Yeah. But it's also a part of the error culture. So there is in principle, one can distinguish between a positive and a negative error culture. In a positive error culture, the expectation is that errors occasionally happen. And if one happens, then you take the error as information in order to find the cause and change things so that the likelihood of the error is going down. In a negative error culture, the assumption is errors must never happen. If one happens, you'll try to hide it. If that doesn't work, then you look for someone guilty. And that's then is the cause of defensive decision-making again. And in that negative error culture, the level of error typically goes on. And it's not being reduced because people are blamed, not the causes are sought. An example for positive error cultures are the international commercial airlines, particularly the cockpit culture. And flying is so safe today, thanks to a number of means like checklists, like critical incidents reporting systems. An example for negative error culture, besides the big corporations, are most hospitals, where errors are made again, and you know that better than I. And you know the estimates in the US. So already in 1999, the Institute of Medicine had estimated that in hospitals alone, between roughly 50 and 100,000 Americans die every year from preventable errors. I've seen new studies, the estimates are now up between 200,000 and 400,000. So you don't have to have any anxiety of terrorists, no. The problem is somewhere else, if these numbers are true. That's the... And positive error cultures is also something that matters in many other fields, like politics. More and more defensive politicians. Now you have at the moment a special character who doesn't fit in any of these categories. And defensive decision-making is also one means to slow down innovation. And so in many areas, so in Germany, doctors need to make more documentation. And in the, as a reaction to the financial crisis, so the customers are asked to go through endless paper in order to estimate the risk, which none of the customers helps. It's only for defensive purposes. And so we have this in many fields. So here is a recipe for slowing down innovation. I apologize for the cut, for somehow it doesn't work here anymore. So 3 ways to slow down innovation. First, always mistrust gut feelings. Second, demand an explanation for every new idea. And promote a negative error culture and lots of documentation to protect yourself. If that sounds familiar for you, you know what you have to change. So there exists positive error culture, and we should use them as models to change our own negative cultures. Or just think what would happen to sports if the negative error cultures would swap over there. And people would have to document everything and reason everything. So I use an example from soccer. So if there is a soccer player who scores a goal from an amazing angle, now think the referee would run to him and say, you explain now how you did it. If you can't, it doesn't count. That's the logic. It's all about justification, no longer about performance. And we are drifting in this line. Okay, and at the end, I brought you a puzzle, which is a special puzzle, just to keep you awake. The puzzle has been given by the psychologist Max Wertheimer to his close friend Albert Einstein, long time ago. And the puzzle is the following. So Max Wertheimer liked to do like teasers and thinking puzzles. And of course, who would be the better subject than his friend, Albert Einstein? And I use this for a specific reason, because negative error cultures, they start with the assumption that we never should make errors. And this is a puzzle where Einstein failed. And it took him some time to find the right solution. So it's a kind of encouragement that this is something very normal that we fail on sometimes. So here's the puzzle. There is a hill. It's 1 mile up and 1 mile down. And there's an old car who can only make 30 miles per hour up because it's a weak car. Question: how fast would the car have to go downhill where it can drive faster in order to have an average speed over the 2 miles, down and up, of 60 miles per hour? Okay, again, it's 2 miles, and the car can only make 30 miles up. How fast would it have to drive down in order to have, for the total stretch of 2 miles, an average speed of 60 miles per hour? Is the problem clear? So, what do you say?
I thought the car could not go 60, at least not in the uphill.
No, it cannot go uphill. But the 60 is for the entire, up and down. That's the question why. So you could say 30, it should do 60, maybe it has to do 90. So it's an average 60. That would be one solution. Or 30 and also 30 down, that makes also 60. Or 30 and 120. Yeah, because it's maybe, yeah. So what's the question? What's the answer? It's an average 30 up, yeah? And also average 60 for the entire distance. 90? Yeah, 30 and 90 makes 120 divided by 2 is 60. That's your bet. You have quick solutions for many problems. But at least quick, yeah? And a solution. Anyone else? Sorry? There's nothing to do with prostate, huh? If that is your question. So I give you a hint, huh? A hint, yeah? How long does it take the car to get up? 2 minutes, yeah? Is this clear? Right. How long does the car take to do 2 miles with an average speed of 60? 2 minutes. Now the answer is clear. It can't do it. Because it takes 2 minutes to get up, and it would need 2 minutes to do the entire distance. So it had to go infinite distance, which was not possible. Einstein wrote to his friend Max Wertheimer that you fooled me. I first calculated, and then only I realized it doesn't work. And then he said, this just proves that we all are quite stupid. So, let me finish. So, I invited you today to a voyage into research on decision-making under risk, under uncertainty, and here are 4 key points. Risk is not the same as uncertainty. The best decision under risk is not the best decision under uncertainty. And you've seen a number of examples. But it's very important because classical decision theory refuses to distinguish between risk and uncertainty and believes that with probability based, otherwise you can solve all problems. It's a big illusion. Second, the adaptive toolbox is the collection of heuristics a person, a leader, or a doctor has in its disposal. And I just learned outside that in your disciplines you use lots of heuristics. It's just you hadn't thought about this in this way. And there might be a good collection for training young doctors. Ecological rationality is the science about finding out and showing under what situations which heuristic would work, and also about less is more effects. The methodology is to be precise, to have precise models, to have competitive testing, and also about prediction, not just explaining everything in the past. And I hoped that this excursion into the science of risk communication, heuristics, and also intuition has inspired you to follow up this way and to think about your own life in maybe new terms. Thank you for your attention. Yeah. So there is still time for some questions, and you just raise your hand and yes.
So you talked a while back about how big data and predictive models don't work that well in the real world, and a lot of the literature nowadays is how artificial intelligence is going to be so important in medicine and in other areas. So do you feel like maybe that's not true, or do you feel like they're going to improve their protocols and whatnot to where it will be very important, let's just say in medicine?
Yeah. So I think the important thing is to ask for evidence, not promises. Promises are all over there. There's very little evidence. And in general, I would suspect that AI and big data will work in situations that are fairly stable. And so in astronomy, it's a big success. There has been big data since centuries collected. But there's little evidence that it works in medicine and in finance. And you cannot exclude that, but you should just ask for evidence. And the evidence is, show me that your algorithm is better than what we already have. That's the comparison. It's competitive. And at best, I would like to see this from an independent institution, because big data is first big business. And often, even if it does something incremental better than what we have, the question is whether we want to waste all this money for that. And there's much to be done. I would first put the money into the education of doctors, of medical students, so that they get risk literate. There's lots to do. Better information for patients. And maybe train young people in schools to be health literate. And that is our powerful intervention, that we should go and not get distracted from some promises in AI. Yes?
Do you have any thoughts about why heuristics work? Is it as simple as the brain making big data calculation, or is it something different? Why do these work?
Why heuristics work? Yeah. So I gave a few examples. Heuristics can work because the environment has a certain structure. So think about the one good reason heuristics you have seen. If all the other cues contribute much, and not more than the first one, then you can prove it, that it's of no point to have a deeper analysis. And the general way to understand this is the bias variance dilemma. The heuristics, they minimize the error due to variance, and in many cases don't increase much biases. And in general, we know that animals, humans, have always relied on heuristics. And optimization is just an ideal that, it's imposed on all of that, like in economics, but it also means that there's no real interest in analyzing what people do or what animals do. And it's also interesting that some of the heuristics that people use, you can find them in animals. Like the gaze heuristic, it's dogs who do it, but also bees, bumblebees, or bats who go after moths. And yeah. And so my standard null hypothesis would be it's a heuristic process. And just think about the calculus was invented not so long time ago. What did everyone do before? Had an intuitive calculus or so? Yeah, I don't think that's it. Yes?
What do you do when your intuition is at odds with one of your your fast and frugal decision trees?
Okay, that's a good question. And in general, there's no single answer. But if you have lots of experience in an area, then you might trust your intuition more than otherwise. There are also conflicts between people. So, for instance, I worked with a group of executives. There were 5. They were leading a bank, and they were in a situation where it was long after midnight. They were thinking about a big business, and 4 were in favor and 1 had a bad gut feeling. What did they do? They asked him, the other one, explain exactly. And of course he cannot explain by definition. So he came up with something, and they killed the argument and sailed into disaster. And now, as they told me, they've learned one thing. So understanding just the definition of an intuition, it makes no sense to ask this guy about why, because he cannot know if he has a bad gut feeling. And we need to ask a different question. We need to ask ourselves, so the other 4, who is the person here who is most experienced with the problem at hand? If it's him, then we look for a different investment. No questions asked. Yeah.
Is there a cognitive process that allows for a person to do check on their intuition so that they modify their intuition over time, or is it just a, is there some kind of insight cognitive process where a person is always checking their intuition to see how good it is historically?
I think it's mostly you check it by the result outside. And there are areas like in sports where you can check all the time. This is why the intuitions are good. In other areas, it may take years.
I mean, I notice some people have just really poor intuition, and that doesn't seem to get better with time. Other people, their intuition changes with time. I mean, it seems cognitively there's a difference between those two types of people.
That there are certainly individual differences, but I do not know any research that have really worked out why. And it's also, we have no evidence. The usual story is women have better intuitions, men are rational.
I was thinking particularly about men who continually get crossed.
About men.
Women.
Yeah. But we do not really have evidence for that. The best evidence is the length of time you have with a problem, but you also need a problem where there's feedback. Yeah. So a radiologist needs feedback. And then he learns seeing, but he cannot explain it, what he's seeing. Yes?
So in training these days, there's a pretty big emphasis on evidence-based decision-making. And I wonder how you reconcile that with the heuristic model, taking the intuition of an individual versus having evidence-based heuristics, and how you propose we come up with something like that that maybe is evidence-based, like is proposed in your examples.
So the heuristics we study, they're all evidence-based. They're tested and they're analyzed. So here there is no difference. So intuitions can sometimes be tested, like as we had to like sports. In other situations, it's hard. If something really takes long time and your life is short. So for instance, marrying, you think about men who marry wives and always get the wrong wife. How many chances does a man have to learn? And then you basically what you need to do is you learn socially from others, from the errors of others. That's the heuristic. Watch your parents. Watch how your siblings are doing and learn from that. That helps.
Yes, sir. I was wondering if you could address evolutionary biology and to what extent that might shape decision-making heuristics, the robustness of persistences.
Yeah. So for heuristics like the gaze heuristic, you need a number of evolved capacities to execute it. For instance, the ability to keep your eye on a moving target. This is a very difficult problem in robotics today. And the robots get better and better, but we have no problem with that. It is an inborn capacity, and as we know, children need to train a little bit. And the best thing what you can do is if you have a toddler, and the toddler is there, put a mobile up there and let him or her, they do it automatically, fixate it. It's going. So they're practicing becoming a baseball player. That's what it is. And evolutionary things, so I haven't dwelled very much with that, but lots of the abilities, like recognition also, is an ability that is so powerful and so amazing, and we just have been equipped with that. And also many of these intuitive capabilities are also amazing. And sometimes in research they're confused with logical errors, which is a basic error. For instance, language understanding is just unbelievably. So how do we know that an and means a logical and or a temporal and? and we switch. And so if the question is, I invited friends and colleagues, it doesn't mean the logical end. It's not the intersection, but it's the logical or. That's considered an error by my friends who like to point out that everyone has a bias. I think it's one of the greatest achievements that we automatically decode the meaning of terms from their context. And it's almost not studied how this works. And that's an ability that we have somehow half inherited and also trained. So I would want to have more evolutionary biologists in that. And there's also a group who works and tries to analyze how animals make decisions, and that's then, of course, heuristics. But biology also has another group who really want to make as-if models, optimization models. So like optimal foraging, and they're split over that. I'm more curious to find out how ants make decisions or bees make decisions, and this is wonderful work. And I'm less interested in making an optimization model and prove how great my mathematics is.
When you were talking about discussing risk with patients in terms of frequency, for example, the drug side effect, 30% chance of getting this risk, you switch the words by saying 3 out of 10 of my patients.
Yeah.
Is that just like manipulation of the wording? I mean, I don't understand that concept. Like, why would you say 30% or 3 out of 10? What's the difference there with the patient?
If you say 30% of my patients, yeah, then I think there's not much difference between 3 out of every 10 of my patients. I still think that it's easier for the average patient to understand 3 out of every 10. The problem with the percentage comes if you attach it as a single event probability. You have a 30% chance. Then it starts where patients understand something. And you are not clearly communicating what reference class you mean. The examples I gave, like probabilities of rain, illustrates that. And there are many others. So in general, I would always use frequencies. Avoid percentages, and there are some cases, if you specify the reference class like 30% of my patients, then you minimize the misunderstanding.
It seems to me that, well, let me ask it this way. With study heuristics, has there been any work with what overconfidence does to kind of blow the accuracy of heuristics up?
To blow the accuracy up means?
So someone who suffers from severe case of overconfidence in all matters, and their accuracy with the heuristics compared to others, is that effective? The results, their whatever the right term is.
I'm not sure whether I understand what you agree. I can answer another question, but so can you try again?
Yeah. Okay. We all know people who are very overconfident in their abilities. Mm-hmm. This degree or level of overconfidence, that the study of results of heuristic analysis, has that been looked at?
Okay.
So it might be a different bias. You should overconfidence as maybe an incorrect term.
So the term overconfidence is used for at least a half a dozen different phenomena. None of this has ever been shown to be logically or empirically connected. That's the first observation. Second is, what's called overconfidence is often not an error at all. So take a very well-known meaning. So people think they're better than average. That's one of the many meanings of overconfidence. So that has been shown by car drivers. So they were asked, "Do you think how well do you think you are driving?" And the majority thinks they drive better than average. Now, The problem with this research is, first, what does this relate to? So if driving better means having fewer accidents, which is one interpretation, it's all open, then it's actually true that most people have fewer accidents than the average number of accidents, because the distribution is highly skewed. So there are many people who have, say, within 10 years, no accident, or one, and then there are those out there whom you don't want to meet on the street. We have many. And if you do the analysis, then you find, actually, I've done this, that with American data, that 80% of the drivers have fewer accidents than the average number of accidents. So there's no error there, because the distribution is skewed. If it would be symmetric, then it would be an error, but it's not. And then you can go around that by asking people about the median. But who knows what a median is among the general population, or percentage? It has also been trained. But then the next problem is, now what does better mean? So so think about teachers. Teachers and professors have been asked, and a similar result, and 80% think they're doing better than the average. And forget the first problem, it's also skewed, the distribution, because it's not symmetrically. But one teacher might think, one professor might think, I have more publications than anyone else here. So that's my experience. The next one thinks, I am beloved by my students. And the third one thinks, I'm getting more grant money than everyone else. So if you don't define that, everyone will define it in the way what he or she actually does. Yeah? And then, of course, you get this thing. Yeah? So many of these experiments are so ambiguous, and instead of clarifying what's going on, you blame people that are irrational. There is, for instance, the other meanings of overconfidence. I've written that, I've studied that. They are mostly illusions by the researchers. So, I don't think I could show you this in detail, but I'll give you a simple example. The overconfidence is typically studied with general knowledge questions. For instance, which city is more south, Rome or New York? What do you say? New York? You? Rome, yeah? How confident are you? And you now need to give a number between 50 and 100. 50? Okay. It's just because he said that. Okay. Anyhow, it's actually New York. But, look, what's happening here is that researchers in decision making, and I know some of them, they went through an almanac to find facts that surprised them, and put these into a confidence questionnaire. And in the case of temperature, is usually a brilliant cue for latitude, but in a few examples, it's not one. And if you take this and over-represent these cases, then people will look overconfident. Now, we have in the 1990s shown that the moment you randomly take, in this case, cities, you take all big cities, then people are straight to the way. And this is built. So here, the overconfidence emerges because the researchers have given unrepresentative samples and looked for the exceptions. And so it goes on. There is a true overconfidence, and this is a pragmatic overconfidence. So if you're an astrologer, you have to be overconfident to get customers. If you predict exchange rates, you have to be overconfident to get it. And if you predict the stock market, the same thing. So, but one should not confuse these things. So there is an entire literature, and I can give you references on that. You find something in this book here on taking these so-called cognitive illusions apart, and most of them just disappear. People aren't as stupid unless they can make money with it.
Our speaker this year is really an exceptional individual. I've had a chance to, he's actually staying with us, so I've had a chance to get to talk with him a little and get to know him. When I try to decide on the speakers to give this lecture, I go through a pretty rigorous process, and I print out all their academic papers, and I get a sense for their body of work before I invite them. And this year it was really hard because his body of work, if you looked at the binder, it's about this thick of papers, and that doesn't include his books. I tend to read the papers instead of the books. But he has the range and the scope of his contribution, to say nothing about the depth of it and the originality of it. It's really quite an incredible contribution. And I know many of you are familiar with quite a bit of his work, and it's really very, very unique because it spans many, many different disciplines: economics, cognitive science, healthcare, finance. There's almost no area where his expertise and his contribution it's just been unbelievably significant. And I think on a personal level, what has helped me, this whole idea of cognitive illusions that we are subject to as clinicians, we have a lot of cognitive illusions, and how he's taught us how to overcome these and deal with them, especially in the framing of our conversations with patients about risk. It is, for those of you who have adopted this in your practice, it is so powerful, so impactful to us as clinicians in learning how to frame conversations with our patients. So it's a tremendous honor to have you here, Gerd, and I think you're going to find a very friendly audience. Please give a warm welcome to Dr. Gegenrenzer.
Thank you. At the beginning of the 20th century, the science fiction author Herbert George Wells wrote in his political work, and he made a prediction. The prediction was, if we want mature and efficient citizens in a modern technological world, we need to teach them three things: reading, writing, and statistical thinking. That is, how to deal with the risks and uncertainties in a technological world. We have managed, almost 100 years later now, to teach almost everyone reading and writing, but not statistical thinking. A news speaker in TV once announced the weather the following way: there is a 50% chance of rain on Saturday, he said, and there is a 50% chance of rain on Sunday. Therefore, he concluded, there is a 100% chance of rain on the weekend. We smile about that, yes. But do you know what it means if you hear on the radio or read on your iPhone that there's a 30% chance of rain tomorrow. 30% of what? Now, I live in Berlin, Germany, and we studied what Berliners think that means. Most Berliners believe a 30% chance of rain means that it will rain tomorrow in 30% of the time. That is 7 to 8 hours. Others think it means it will rain in 30% of the region. That is most likely not where I live. Most New Yorkers we have studied think that's all wrong. It means something third, namely that it will rain on 30% of the days for which this prediction has been made. That is, tomorrow, most likely not at all. Are people stupid? Now, some of my colleagues have come to this conclusion. But the problem is not just in the individual mind, it's also in the experts who have never learned to communicate statistical information in an understandable way. What the meteorologists want to say is that it will rain on 30% of the days where the prediction has been made. They could say that, but have never learned to say this. And there is a simple solution to this problem. Always ask percentage of what? So is it days, time, or region? And you have some imagination, you can think about other reference classes too. For instance, one woman in Athens told us, I know what 30% chance of rain means. 3 meteorologists think it rains and 7 not. So what I want to do in this first lecture is to invite you to a voyage into how to communicate risk and deal with risk. In the second lecture, after a break, we will do more with uncertainty, where the risks are not known. So the general idea is the following. There is first, understanding and communicating risk is essential for almost everyone. It's particularly essential for doctors. Second, almost nobody in our Western countries is ever being taught. And then we get this confusion. So not knowing what a 30% chance of rain is not a big thing. You just make it wet. But there are other things where it really matters. And third, if you read books written by people who tell you you are predictably irrational and hopeless too, don't believe that. We can teach people to understand these things. And we don't need to nudge them into some behavior. And it's very important that we need to change the way we teach in our schools. We need to make young people risk literate, and we need to make doctors risk literate and patients. Otherwise, we will not ever live up to the dream that Herbert George Wells had, that there might be a kind of enlightened citizenship. If you don't understand numbers, it's something like if you don't understand how to read and write. So, what I want to do now with you is to give you a few examples from broad aspects, and then in the major part of the lecture focus on helping doctors and patients make sense of health statistics. That's the plan. Are you ready? Well, let's start. So, let me start with a very simple example. Some time ago, the news reported during the vacation seaon that shark attacks has risen by 100%. Now, what do you do if you're on the beach? Do you let your children still swim? Or do you still surf? 100%. Now, what does 100% mean? The last year, the year before, the number of deadly shark attacks worldwide was 6. This year, when it was reported, it was 8. Sorry, it was 12. So 6 more. It's always around 10. There is nothing, no animal I know of that kills fewer people than sharks. If you know one, let me know. And this is the difference between a relative risk and an absolute risk. So the absolute risk is the absolute number, 6 more. So from 6 to 12. The relative risk is 100% more. You understand the point? So that's the second lesson. Always communicate or ask for absolute risk increases or reductions. Never accept relative risks. So if you have heard about a few weeks ago, the news went through the journals that a study in Lancet has shown that even a single drink a day, like a glass of wine or of beer, increases the chances that you get one of some 20 diseases by 0.5%. You might think that 0.5% doesn't sound big, but it is 0.5%. So do you still drink alcohol? Now, what is the 0.5%? It's a relative risk increase. And what is the absolute increase? That's the question to ask. So in the original study, the absolute increase was not reported. Lancet has a policy that says that every study should reveal the absolute risk increase or decreases. The authors didn't. The editor didn't notice or didn't know the rules, and it was published. The only one who paid attention was the press department of Lancet, and before they did the press release, they insisted that the authors reveal what the absolute risk increase is. Now, it was, you have 100,000 people who don't drink alcohol, and 100,000 who drink 1 drink a day. In the first group, 10 years later or so, there are 914 who get any of these many diseases they were looking for. And in the 1 drink a day group, it increased from 914 in 100,000 to 918. See that? That's 4 in 100,000. So that's not 0.5%. So 0.5% more is the same as 0.004%. If they, now you can ask, why don't they report that? And there are several reasons. It doesn't create much attention, if you're honest. And relative numbers create attention and fear and anxiety, or stop drinking. And another reason is that many people don't know the difference and actually are not asking the questions. Show me the absolute risk. Now, let's go on our voyage from the Lancet into Great Britain. And I'm making the same point again with a different example, just in order to get it into your minds. I want you to leave this room totally enlightened, so that nobody can manipulate you anymore. The only person who can manipulate then are you. you can manipulate others, but if everyone other knows about that, then it's the end of all of that. And while we can do some things, but not really control, as the Lancet example says, if even the guidelines don't help, the one solution is to make everyone risk literate, and then it doesn't help. So now we are in the UK. Great Britain has many traditions, like scones, tea, the Queen, but also the contraceptive pill scare. Every few years, women are alarmed that by taking the pill, the contraceptive pill, they increase the risk of getting a thrombosis, a potentially life-threatening situation. The most famous of these scares went this way. The UK Department for the Safety of Medicine announced an emergency press conference, and in this press conference it declared to the journalist that a study had shown that women who take the third generation pill increase their risk of thrombosis by 100%. Can't be more, or it's almost certain. Many British women thought so and panicked, stopped taking the pill, which led to unwanted pregnancies and abortions. How much is 100%? Now, the study had shown that out of every 7,000 women who took the pill of the previous generation, one got a thrombosis, and out of every 7,000 who took the pill of the new generation, that increased from 1 to 2. So, from 1 to 2 in 7,000, that's an absolute risk. But you can report it as a relative risk increase, then you have 100%. If the press and also the UK Committee for Safety of Medicines would have reported the absolute risk, nobody would have cared very much. But this single announcement had the consequences that in the following year there were about 13,000 abortions more than usual in England and Wales, and also as many more pregnancies as usual. And again, that could be avoided in a very simple way if everyone would be taught the difference between an absolute and a relative risk. So if every woman would have asked, tell me what the absolute risk is. The only ones who really made profit were the journalists who got the story on the first page here of the Sunday Times magazine. And you can read here, the title is Kiss of Death. Is the pill doomed? The risk is doubled, 100% more. So here you have also a very interesting instance. We often think that our emotions they come from inside, but they're actually manipulated from outside with the help of our inability or our innumeracy. And we are not talking about getting a degree in statistics. We are talking about elementary things that are at the level like elementary reading abilities. And we tolerate a society where this is not being taught. I give you a final example about the relationship between emotions and statistical thinking before we get in the more healthcare part. Okay, most of you will remember this picture. This is the 2011, 9/11/2001, and we think we know everything about what happened then. But what did Americans do after the attack? We know that many stopped flying. So did these people stay home or jump into their cars? I analyzed the road statistics in the US and found that for 12 months after 9/11, the miles driven increased by about 5%, and mostly where one is traveling long distance, so the interstate highways. And during that time, an estimated 1,600 Americans died on the roads in the attempt to avoid the risk of flying. That means 1,600 more than usual. What you see here is the analysis. That's the number of fatal crashes above and below monthly average, and that's the time. The reason why this is normalized is because every month has a different base rate of deadly accidents. By the way, do you know in which month has or causes or has the fewest number of people dying on the road? So which is the safest month? What do you think? February, right? And why? Right, it has only 28 days. Huh? That's the answer. Huh? Good thinker. And so that's why it's normalized. And the zero corresponds at this time to about 3,500 people who die per month on the roads. And you can see that in the time before 9/11, that's the red line, it was always around 100 plus, 100 less. And then for 12 months after 9/11, every year it was more, that's the red line, than the average of the last 5 years. And also mostly more than the entire variability in the last 5 years. And then it went back to normal. And that's the roughly estimated 1,000 Americans who died on the road. This is more than the number of people in the 4 fatal flights together. So, terrorists strike twice. The first time with physical force, like flying the plane into the Twin Towers. The second time, they strike with the help of our brains, with our anxieties. What is the anxiety that terrorists exploit? I call it dread risk. So these are situations where many people suddenly die, so, or at least in a short time, like plane crashes. It is very difficult to elicit our anxiety for situations where as many people or more die distributed over the year, as in car driving, motorcycle driving, smoking. Has anyone anxiety sitting in a car? No. And so the difference is that the moment it is a dread risk, so many people die together, then the anxiety can be easily elicited. In other words, we fear dying together with others. We don't fear dying alone. And and this is happening again and again and again, also in catastrophes that never occurred. So remember swine flu, bird flu, mad cow disease, and Ebola, all kinds of things where we feared, like in mad cow disease, where we feared to bite into a good steak, and now it's okay again. And so in the case of mad cow disease, so what do you think? How many people, I only know the numbers from Europe, how many people died in all of Europe within 10 years on the consequences of mad cow disease, so the Creutzfeldt-Jakob variant. So what do you think? How many people died? What was this fuss all about? So the announcement was that 100,000 died. Really, what died were about 150. 150, that's all. Do you know what other cause of death caused about 150 people to die in the same time in all over Europe? The drinking of no. So it was the drinking of perfumed lamp oil. So that's parents who like a certain kind of lighting, and children think it's like lemonade. It smells like that, it looks like that, huh? And it's all children who died. But nobody paid attention. These children die distributed over the year, and that's not a dread risk. If these 150 children would have died on one day, hell would be loose. So this is an example about to understand how one's own anxieties are guided from outside. So the remote control is outside, and terrorists use it. And by the way, I know in Germany where I live, anxiety of terrorists is about as high or almost as high as in this country. But do you know what the effects are? And all of us are being remote controlled on that. So in Germany, it's more likely that one dies from lightning than from a terrorist, despite the attacks in Berlin. In the US, it's more likely that someone is shot by a toddler than by a terrorist. A toddler who plays with daddy's darling weapons. So just as a kind of thing. And it's very important, I believe, that we take the remote control of our emotions again in our own hands. And even if we feel anxiety, we have a brain and think, I'm not tolerating a second strike. And I'm flying. I'm not. And even if you have a little bit trembling on that, that's how your emotions are being worked on. But we can overcome that. So, in that first part, I gave you a few examples, mainly showing that risk literacy is important, and also that's linked to our emotions. And we often fear the wrong things. Like terrorism, fear of terrorism is one of those. That's the most unlikely thing that will kill you. I don't know, it's more likely than sharks, but it's close to that. And we need to pay attention and what the real risks are. So I turn now to healthcare. And I will make the following argument. First, most doctors and patients do not understand health statistics. And I emphasize doctors and patients. It's not just patients. The causes are not in the brain of physicians. Physicians are intelligent people. The causes are first in medical schools. Medical schools all over the world, with very few exceptions, fail in teaching statistical thinking. They may teach biostatistics, but usually biostatistics enters here and exits there immediately. I don't know what your experience was with biostatistics. The most medical students I talk to have no idea how this connects to healthcare. And many biostatisticians are not even aware of that. So here's a story. I recently gave a talk to the Austrian Chamber of Physicians and explained about this issue, about the lack of training of physicians and the failure of the medical departments. After the talk, a man raised his hand in the discussion situation and he said, I am the professor of biostatistics at the Medical University of Vienna. And what you told us may be true in Berlin or in New York, but not in Vienna. I take care of that. My students understand health statistics. I responded, I said, I can only congratulate you. I know no other department that was obviously so successful as you, but yeah, good. Then a young woman raised her hand and stood up and said, I would like to say the following. I was a student of the professor, and we understood nothing. So, failure of medical schools to teach. Second, biased reporting in medical journals and down in press releases and down to the journalists. And we had an example, reporting a relative risk, 100% not reporting the absolute risk. And then also lack of education of the public. We also have failed to teach statistical thinking in school. And then we have patients who don't even know what questions to ask. So there's a solution to that problem. Not every problem has a solution, but this one has one. First, teach risk literacy in medical school. And I myself, and also in continuing medical education, I've trained about 1,000 doctors in medical education. And my experience is that most doctors are grateful because finally they begin to understand things and have not to muddle through and avoid patients' questions. Second, we need to implement transparent risk communication in journals, in the media. And the editors need to get their act together and not allow, or in the case of Lancet that I mentioned, or insist that the rules are also implemented. And finally, the solution that really would be the most sustainable is teach health literacy in school, starting in first grade, in a playful way. Don't teach mathematics or statistics as mathematics, but teach it with examples. So that, and it always helps young people when they are explained how the adults are being misled. So finally, the 8-year-old goes home and asks Daddy, what do you think when you hear there's a 30% chance of rain? And the daddy has no idea. That's a wonderful way to teach and to make them competent. So the first distinction I want to make is already mentioned, but I want to get deeper, between relative and absolute risks. I think all of you now know what relative and absolute risks are. We'll see. I will use the case of mammography screening as an example. Mammography screening is about women. And women have been in the history dealt like children, most of the time. And I show you a poster from the American Cancer Society from the 1980s, not so long ago. And the poster explains women about mammography screening. And it reads, if you haven't had a mammogram, you need more than your breasts examined. There is no fact in the entire things. There's nothing about benefits, nothing about harms. It's just a kind of insult. Now, you won't see this anymore today. But today, women are misled by statistics. And relative and absolute risk is one of the trick. Women are being misled. So, you may know that the randomized studies showed that this includes, about 500,000 women. So, that out of those, say, every 1,000 who do not participate in screening age 50 plus, 10 years later, 5 die from breast cancer. And out of 1,000 who participate, it's 4. That's an absolute risk reduction of 5 to 4 in every 1,000, so 1 in 1,000. Yeah? The other 999 have no benefit, only potential problems. How would you communicate that effect to women in order to make the benefit of mammography screening appear bigger? Yeah, what would you say? 20% reduction. So women who participate in screening reduce their chance of dying from breast cancer by 20%. Now, I'll give you a few examples.
You should do the opposite. Say they have a 25% more chance of dying, because 25 is even more convincing than 20%.
Yeah, but not of more dying. No. No, you're not getting women to go there and increase that. As you just, yeah. But I see what you mean, yeah? His point is that from 4 to 5 is 25%, and from 5 to 4 is, but it's not even necessary. I'll give you a few examples from the UK, how this risk is communicated in pamphlets on mammography screening. So, here's the Welsh NH leaflet, breast cancer. Breast screening has been shown to reduce the risk of dying from breast cancer by around 35%. So that's the 1 in 1,000. You don't need your sophistication, actually. Just and the 20% rounded up to 35. Then we have the New Zealand Breast Cancer Foundation saying screening mammograms reduce the chance by dying from breast cancer by approximately 33%. Well, 20% rounded up to 33. There is no mentioning of the absolute risk reductions in these leaflets. And one counts on that women don't know the difference and believe that, oh, that means out of 100 women, 35, his life will be saved. Isn't that? Hear that? So we and others have pushed in Europe that women get the absolute risk reduction and not the relative. And the NHH has finally responded to that, but read what they say. Screening saves about 1 life from breast cancer from every 200 women who are screened. Now we do have absolute numbers, no relative, but the numbers are wrong. The numbers are rounded up. From 1 in 1,000 to 1 in 200, and that's the same from 1 in 1,000 to 5 in 1,000. Yeah? There's no evidence for this number, 5 in 1,000, but you always can do model calculations. And that gets there. It's a long way to fight that women have the right to actually get the information of the randomized trials. How can one do that? So we design at the Harding Center for Risk Literacy at the Max Planck Institute so-called fact boxes. Here's one for breast cancer screening. A fact box summarizes the entire evidence available. The reference is given at the bottom, typically from a Cochrane review, but doesn't use any misleading statistics. There's no relative risks, there is no 5-year survival rates, they're just absolute numbers. And it's set up in a way that you have 2 columns. So there's also a text to that, which I haven't here, that explains it. So women age 50 or older. So you take 1,000 women from all these studies and 1,000 women who have no screening and 1,000 who have screening, and ask what happens 10 years later. And in the rows, there are not only the benefits, there are also the harms. The harms are usually not talked about. And breast cancer mortality is here. So in the no screening group, so on average, 5 women die from breast cancer 10 years later. And in the screening group, it's 4. That's what we had about. More important or equally important is total cancer mortality. The reason is one does not know always from what cause a person died, and many unlucky people have multiple cancers. So the total cancer mortality is a more reliable number. And as you can see, it's equal. So that means the one woman in the screening group who dies more from breast cancer, there's another one who dies more from another cancer. So there is no life saved here. Also, what's not shown here, the total mortality is also exactly the same. And you probably will rarely have ever heard about total cancer mortality or total mortality, and the reason is obvious, because that is not something that would convince too many women to undergo that. Then there are harms. And there are basically two kinds of harms, namely women who do not have breast cancer and get false positives, and then often biopsies. And that happens to many. One doesn't know exactly, 50 to 200. There's an interesting reason why the numbers for benefits are precise and the number for harms are so wide. Can you think why? Because most studies don't report harms at all. And then one gets these small samples. And the second harm is for women who do have breast cancer, but a non-progressive version. That is something that is technically breast cancer, but clinically irrelevant. So as many ductal carcinoma in situ are of this kind. So that means these women would have never noticed during their lifetime that they have this little change in the cell structure, and would be happily lived, but if mammography detects it, then they might end up with a lumpectomy or mastectomy, totally unnecessary. So, and that's an estimated between 2 and 10 in every 1,000 women. So this is what a fact book does. The fact box provides the information that's available at some point in time in an understandable way, and benefits and harms, so that every person can make up their own mind. There is no recommendation here. We do not want to continue the paternalism that has been there, and I think every adult person can make up her own mind. And if you can't, then you might be lucky and have a husband who also helps along thinking, or your friends. So anyhow, the studies we have done with fact boxes is to show they change the understanding and often also the decisions. So in one case, I had a gynecologist who always had recommended mammography screening, and as many of them didn't know the evidence. When he checked the evidence, he changed his way and actually used a fact box in order to inform his female patients. And he said, at the end, a third of them said, I'll want to do it nevertheless. A third said, in no case, why would I do this? And a third said, okay, ask me again in 5 years. So delayed decision making, but that's fine. At least we have informed decision making, and that's as far we want to get. So the what do you think does the general public know about the benefit of cancer screening? And I focus here on mammography screening for women and what men know of PSA screening. What do you think? I mean, almost everyone talks about these two screenings, so that should be that everyone is well informed. We have done the first Europe-wide study, and in 9 countries, with over 10,000 people representatively selected, and asked them about the benefit, so men about the benefit of PSA screening and women about the benefit of mammography screening. We only asked about breast cancer mortality because of the total cancer mortality, the information is being withheld. So the best answer would be 1 in 1,000. And I show you now, what do you think? In which country are women have the best estimates of the benefit? I give you the countries, all large countries in Europe. So it's Germany, UK, France, Italy, Spain, the Netherlands, the Austria, Poland, and the European part of Russia. There's one country. So the general result is, I will show it immediately, most women overestimate the benefits by orders of magnitudes. They have been misled. They think the 20% or 30% means like 300 out of 1,000. But there is one country who stands out, is much better than every other country. What do you think? Which of these countries? Russia. Why do you think that? Yes, you're right. It's the Russian women who by far get the best estimates, and not because they got more information, but because they got less information and less meeting information. That's what you see here. Yellow means that the estimates are, in that case, something between 0 and 10 in 1,000. Yeah? And the red one is overestimation by a factor of 10, 100 more, I don't know. So most women estimate the benefit as around 100 to 200 in every 1,000. And that's probably the relative risk reduction that comes in here. And you see the Germans don't do very well, but also the men are not better. Men are equally misled, and the best one is again Russia. Spain does a little bit good. There's no study in the US. You can do one. I would not bet that you're better than the Russians. Yes?
Has it been decided that they don't have as much information, or they don't trust the information?
It's both. They don't have as much information, and you're right. Russians are much more mistrustful to doctors than Americans. Yeah. They get the information from their family. They trust their family. Yeah. So that's about the state. The red areas here signal how effective the misinformation campaign has been all over Europe. The same trick with relative risk is used in advertisement of medication. Here's Lipitor. And what you read here, Lipitor reduced the risk of stroke by 48%, almost half. Isn't that impressive? That means that out of 100 people who take it, 48 are being saved. Doesn't it mean that? Yeah, so we think, it's again a relative risk. It's not an absolute risk. If an absolute, that would be right. And if you look into the original article, you find the answer. It's a reduction from 2.8 in 100 to 1.5 in 100. So roughly from 2 to 1 in 100. So that's the 50%. But it's sold as 50%. So if you look carefully in the own journals that you read or the pamphlets, you will find many, many, many more of these examples. And also, it's not just advertisement. The misleading statistics, they start already in the top journals. So one trick is to, in a journal, or put it this way, assume you write a paper and you report about a certain medication, and you report about the benefits and the harms. How would you report the harms, and how would you report the benefits in order to sell your product? The harms in absolute, exactly, and the other as a big, because absolute numbers are small, and relative numbers are big and impressive. Now, that's called mismatch framing or speaking double tongue. Now, a study in the BMJ, the JAMA, and the Lancet from 2004 to 2006 found this single trick used in 1 out of every 3 studies. And it's typically that you get the relative risk reduction in the abstract, and the information about the harms comes late in the paper, and is played down. It's just 1%. And that's presented in absolute numbers. And the consequence is, of course, that journal editors should not tolerate misleading statistics, such as we have not gotten yet to survival rates, but we'll get there, and relative risk and mismatch framing. But journal editors are under substantial commercial pressure. And when a press release announces that a medication reduced the probability of getting, say a stroke by 50%, that's big news. But it's 1 percentage point, it's not. So we need also be more honest. And during the more and more commercialization of medicine and healthcare, we are misleading patients more and more. And the question is, for me, medicine is not a business. Medicine is a profession or a calling. And you still can earn enough money. But you don't need 3 sailboats. And we are risking, if these things become known to the general public, then the risk is that doctors end up where bankers are now. Trust is broken, and to repair it takes a long time. So that was the first part. And the point is, insist on absolute risk reductions or increases and reject relative ones. And keep your eyes open. And particularly if you're a journal editor, you should do that. Yes?
So that 48% of the Lipitor, where did that come from? Just made up? Or
Where does what come from?
the Lipitor, the reducing...
On the previous slide.
Oh.
48% came from where?
It was from the 2.8 to 1.5.
Okay, if you calculate the risk reduction from 2.8 down to, and 2.8 is 40% less. See this? Yeah, but good that you ask. That's the way it's done. It's the same like the 100% that we had before. So, I'm going on to a second way to mislead you and everyone. That's the use of 5-year survival rates in order to document the benefits of screening. And mortality rates are clear. When Rudy Giuliani wanted to become the president of the United States some time ago, he told in an interview, I had prostate cancer 5-6 years ago. My chances of surviving prostate cancer, and thank God I was cured of it, in the United States, 82%. My chances of surviving prostate cancer in England, only 44% under socialized medicine. That's what the British have and deserve. Only 44%. Now, however you think about socialized medicine, 82 is more than 44. There's no doubt about that. Huh? So you better, if you're a man, you live in New York and not in York, where they have bad medicine. Yeah. By the way, then Chancellor Tony Blair was also writing about, we have all these bad 5-year survival rates in cancer screening. And it not only Rudy Giuliani misled the public and probably himself, but also other politicians like Tony Blair didn't get the point. The point is, at the time when Rudy Giuliani made this statement, the mortality rates from prostate cancer were about the same in the US and England. So how can it be that mortality is the same, but 5-year survival is double? The answer is there's no correlation between differences in 5-year survival rates, like US and England, and differences in mortality across all solid tumors. In other words, 5-year survival rates are irrelevant information. And I explain now why. One reason is the lead time bias. Assume you have a group of men who all have invasive prostate cancer and die at age 70. The top group are those who don't go screening. That would be more the men in the UK. They're not as pushed into screening like in this country. And so cancer starts. The cancer is detected late because they don't go screening. Say at age 67. They die at age 70. What is the 5-year survival rate? 0. Now the same group of men go screening, cancer starts again, then it's detected early, say at age 60, they die at age 70, what is the 5-year survival rate? 100%. So, in other ways, screening prolongs, but not life. By the time something has been detected. In the other. There's a second reason, besides lead time bias, that's called overdiagnosis. Overdiagnosis can be explained in the same way. There are 1,000 men with progressive prostate cancer on the top, and they're not going screening. 5 years later, say 44% of them are still alive. The others are dead. Now look at people or men who go screening, and not every one of those who have cancer has a progressive prostate cancer, but most prostate cancers are non-progressive. So just to make it simple, there are 1,000 people with progressive and 1,000 men with non-progressive. Those who have non-progressive prostate cancer don't die by definition from prostate cancer, but they enter the formula. So these 2,000 enter the denominator and the numerator. And now, instead of 440 divided by 1,000, you have 2,440 divided by 3,000, and that's roughly Rudy Giuliani's number, 81%. See that? That's called overdiagnosis. You diagnose prostate cancer that's technically prostate cancer, but clinically irrelevant in the sense that the person would die with the cancer, not from. So if the man among you, if you are lucky to live a long life, then you likely get prostate cancer. It's a good sign. Yeah. So rough estimates are, for the US, and they are really rough because nobody knows exactly, that if you have a group of 5 men who are in their 50s, one of them will have prostate cancer. Now you wait 10 years until these 5 men are in their 60s, it will be 2 of them who have prostate cancer. Then you wait another 10 years until they're in their 70s. Now it's 3 of them who have prostate cancer. And if they're lucky to get old and still are alive, in their 80s, it's about 4 of every 5 who have prostate cancer. Only 3% of American men die from prostate cancer. If everyone would be screened, and since most of the 70 and also 60 and 80-year-olds do have some of this, we would have a mass of men who undergo treatment, a treatment that doesn't help them. And the pampers industry would love that, would make big businesses, and as far as I'm informed, they actually support prostate cancer self-help groups. So in order to inspire other men to go into screening, and then, we get that. So Richard Ablin is a professor of medicine who has discovered PSA. And he has given an interview to the New York Times where he said the following: no man should take routine PSA screening. The test was meant for a control after an operation, not before. And he continued, he said, I had never imagined that my discovery 40 years ago would end up in such a profit-driven health disaster for men. All these men were incontinent, impotent. He's also written a book on that called The Great Prostate Hoax. If I make some of you uneasy, that's, and sleepless this night, that's why I'm here. Sorry? Okay. Now let's go to the doctors. Do doctors understand that 5-year survival rates are not diagnostic for mortality and for the benefit of screening? So I just explained that, and I think that should be easy to be taught in medical school. So we did the first study in Germany and the first study in the US that's ever been done. And I'll show you just first the German doctors, and we gave them real information about the European prostate cancer trial, and once in forms of 5-year survival rates in the screening and in the control arm, just like Rudy Giuliani. And second, in mortality differences, which are small. So when we gave the information and framed as survival rates, 5-year survival rates, 97% of these internal medicine physicians believe that screening is effective. They should have said, this information doesn't tell me anything. But if they got the same information in mortality rates, only 5% judged screening as effective. So that shows that you can, about 3/4 of the doctors, you can manipulate them by framing the benefit either as 5-year survival or as mortality rate. And I do not notice it. We also asked him what lead time bias means, and only 2 out of the 65 doctors understood that. And we asked about overdiagnosis. None of them could answer that. That just illustrates the failure of teaching in German medical schools. Do you think that American doctors do better? So in the US, this is a convenient sample. In the US, we had a stratified random sample and gave them the same question, and you can see there's a similar difference between survival rates, then I think that's big, and mortality rates, it's low. The only difference is that here there are still 28% who think it's big. In German, it's only 5%. Yeah? This is a country where intervention is beloved. Here we also asked, what proves that a cancer screening test saves lives? And the first question was, the first alternative was that screen-detected cancers have a better 5-year survival, which is irrelevant, but 76, 3/4 believe that. The correct answer is the third one, that mortality rates are lower among screening persons, so in the randomized trials. That's understood by 81%, but there's still 19% who not even get that point. The most surprising thing was the answers to the question 2, namely, what proves that a cancer screening test saves lives? That more cancers are detected. That doesn't prove that it saves any lives. But almost half of American doctors in this sample of 412 primary care physicians believe that just detecting saves lives. What that shows again, the medical schools in the US fail. Teaching thinking. That's basic thinking. We should not teach our students learning by heart. That's not really needed so much in the world of internet, but we need to teach them thinking. That's the difficult thing to learn at the internet. So the trick with the 5-year survival rate is exploited by many organizations. So short, we know that most doctors don't understand this, so we give them the 5-year survival rate. This is an example from MD Anderson, one of the most respected cancer centers in the US. And look at the graph. What you see here is, on the time scale, that the 5-year survival rates, that's the orange bars, impressively has increased over time. And then the text tells us, compared to the national averages, that's the blue curve. See that? And the blue curve doesn't make much movement. They added a very nice twist at the end there, where there's no evidence that it looks also going down. But that's cosmetics. But the real point is the following. If you look closely, then you find that MD Anderson, if you can read that, that's overall survival. That's 5-year survival rates. But this here is not the national average of 5-year survival rate. It's the national average of mortality rates. See that? And they're not correlated with that. So they don't move very much anyhow, because it's not effective very much. So this is, the text then tells you that more effective radiation therapy and surgery have contributed to the overall increase in longevity. There's no overall increase in longevity because survival rates do not correlate with longevity. With chemotherapy and hormone treatments now playing an increasing role in the treatment of prostate cancer, and so on. I think it's a shame that respected organizations use this trick to mislead men. But if nobody notices, it's fine. And progress is promised, and people want to see progress. You have a question?
Can we frame this in more patients that are diagnosed with false positives are being treated, and there's more likelihood of better survival with someone that didn't have the disease to begin with? Is that?
Yeah, there's overdiagnosis involved. So more men who have a non-progressive cancer are detected and treated, and they wouldn't have died by definition from. But they survived. Yeah, wonderful. Yeah, that's over-treatment, and then there's the other reason I had just for this are these two reasons. Oops, that's the wrong direction. Overdiagnosis, that's your point, and also lead time bias. That's the 2 points. So, 5-year survival rates are not only used to impress men, but also women. Here we have Susan G. Komen. I think they invented the pink ribbon business. That's the idea, yeah? You give women not information, but teddy bears and pink ribbons. That's how you can deal with them. Huh? So just read this carefully. It says, what's key to surviving breast cancer? You. Whatever that means. Huh? But then it says, get screened now. That's the old paternalism. Huh? Women go screening. And many women are under high pressure to go screening, not only from doctors, but also from their own friends. So a colleague of mine who teaches medical statistics in an American university told me that she knows the evidence, she doesn't want to go, but she has no choice and go screening, because otherwise she would lose her female friends who have a kind of religion over mammography screening. And if she deviates from that, she's no longer their friend. That's her motivation. In that case, here, this advertisement has actually information. So that's unusual about numbers, and you see the numbers here. I read it. It says it says early detection saves lives, which is not true. Only lives from breast cancer. The 5-year survival rate for breast cancer when caught early is 98%. When it's not, 23%. So you better go. So the 1 in 1,000 is now a difference between 98 and 23%. See that? And donations appear to increase. Yeah. Isn't that interesting? Huh? You misinform people and you get more money. Yeah. Now, it's not just organizations like Susan G. Komen who live on your donations, but it's also the World Health Organization, or parts of the World Health Organization. That is the statement on mammography screening from 2014. And I read that. In resource-poor settings, the majority of women with breast cancer are diagnosed at an advanced stage of disease. So that's a kind of message, get early. Their 5-year survival rates are low, from 10 to 40%. In settings where the early detection and basic treatments are available and accessible, the 5-year survival rates for early localized breast cancer exceeds 80%. It's a scandal that the World Health Organization uses the old trick with 5-year survival rates to mislead women. And the World Health Organization has many divisions, so that is not a critique of the society, but on those who have written that. Now, the interesting thing is that we live now in a digital age where information flows, particularly about health, and where we have access to every information. The key problem of the digital age is if we are statistically illiterate, then digital just is another source to mislead us. And Microsoft has announced last year, actually 2 years ago, I wrote about that last year, that they have a big data analytics program that saves lives from pancreatic cancer. So imagine it's the situation. It's very much like Google Flu Trends. So you enter search terms and you are on Bing, on Microsoft. You enter search terms and they're being analyzed, and one day you sit there and write a nice paper or email to a friend, and then suddenly a window pops up and says, attention, you may have pancreas cancer. Immediately visit your doctor. Just think about your mood you're in. And that's from the paper that I have published. They used a retrospective study of over 6 million users of Bing. And I'll just give you the, what you can find again here are the 5-year survival rates, which don't tell you anything about the benefit of this program, of any screening. And the New York Times naively repeated that, so that the study suggested early screening can increase the 5-year survival rates of pancreatic patients to 5 to 7%. Every screening increases the 5-year survival rates, even if it doesn't help. It's just more people being detected because of the lead time bias and overdiagnosis. The Microsoft also works with the typical misleading statistics. So 5-year survival rates. Then you may see there is an extremely low false positive rate claimed for the big data program. A false positive rate that you only have in things like HIV testing. And I would be totally surprised that they would have like a false positive rate of only 1 in 10,000. But let's assume that would be true. But does the extremely low false positive rates actually mean that users who get the bad news on the window are really falsely alarmed? No. What they didn't report is the positive predictive value. And you don't find that in the publication because it's no longer as convincing. You can make a simple calculation. Think about 100,000 users. 10 of them, that's roughly a good estimate, have undetected pancreas cancer. According to their own paper, among 10, 1 cancer is detected, 9 are missed. That's about how good it is. Given a false positive rate of 1 in 10,000, we have 10 more false alarms. So we have 11 who test positive, and only 1 of them has actually the cancer. That's the situation. This is the important statistic, but it's not mentioned in that. By the way, I never heard anything more about that. And it seems to be that Microsoft's attempt to prove its usefulness in healthcare went down the hill just like Google flu trend went down the hill. Do you know the Google flu trend story? No? Okay, I'll tell you this at the beginning of next talk. Yeah? It's also telling. So here's a summary of what I've said so far. So we're talking about the art of confusing risk communication. How to confuse others. First, report probabilities for singular events. That was at the very beginning. So the probabilities for 30% chance of rain. And there are also many events, singular events, that are relevant for healthcare. I'll give you one example. A friend of mine is a psychiatrist. He used to have many mildly depressive patients, like many academics. And he prescribed them Prozac, an antidepressive. And he always told them that Prozac has side effects in the sexual domain, like impotence or loss of libido. But the point is, how did he tell them? He said his patients, I need to tell you, if you take Prozac, so you have a 30 to 50% chance of getting one of these side effects. The patient didn't like to hear that. But he also told me they didn't really ask. So when he learned about our research at the Max Planck Institute in Berlin, he noticed, oh, I'm telling them a single event probability that you have a 30 to 50% chance. And I'm not clarifying the reference class. And the patient may think about something totally different. So then he changed the way he communicated the side effect. He said the following, namely what he meant. He said, I need to tell you, if you take Prozac, about 3 to 5 of every 10 of my patients report one of these problems. Then he asked the patients, how did you understand what I had told you before, the 30 to 50%? And many of the patients reported, oh, I had thought that in 30 to 50% of my sexual encounters, something is going wrong. And see the difference? The psychiatrist thinks, as the reference class, he thinks about his patients as the reference class, but doesn't say it. The patients don't think about other patients, they think about themselves. And there's a big difference between that 3 to 5 out of every 10 patients get one of the side effects, and that someone has a 30 to 50% chance in his own sexual encounters. So if you're a person who lives on the sunny side of your life, you are not concerned if your doctor tells you that 3 to 5 of his patients get a problem, because it's the others, it's not you. But if you hear that 30 to 50% of your own encounters go wrong, then it's you. So, and single event probabilities are common in communication in healthcare, and you need to be really cautious about that, and always use frequencies, because a frequency carries the reference class along. If you say 3 to 5 people out of, now what? 10 of my patients, then it's there. The second way to confuse your own patients is report relative risk without baseline risks. So relative risks, and if you would report the baseline, then you're basically by absolute risks. And relative risks, RRR, makes benefits look much more impressive, and also harms look much more frightening. Think about the sharks or the contraceptive pill. Then the next trick is to speak double tongue, report benefits in big numbers and harms in small numbers, and finally report 5-year survival rates instead of mortality rates. So even if a screening has no benefit at all, the 5-year survival rates will be impressive. That's the thing. By the way, there was a study in the BMJ last year by Prasad et al., who had looked at all cancer screenings and asked the question, what evidence do we have that it saved lives? And they were reporting that there are about a half a dozen who reduced the cancer-specific mortality as mammogram, and also as so the FOB tests and sigmoidoscopy and a few others. But there's none where we have evidence that it saves a life, so that it reduces total mortality or total cancer mortality, just as an information. And then you can make up your own mind. In my opinion, we could save lots of money if we would, or we could invest all of this money somewhere where it's proven that it's useful for our health. And that's not the case with cancer screening. It's big business. So we move on to conditional probabilities versus natural frequencies, another distinction. A conditional probability is the probability of A given B. And many people confuse that with B given A. So I give you an example. So it's easy to see. The interesting thing is that the confusion happens in certain contexts and not in others. It's very easy to see that the probability that a randomly drawn man in the US is the president of the US is low. But the probability that someone is a man, given he is the president of the US, is quite high. So here we see that. And the interesting question is why we don't see this in so many other contexts. And I give you an example from another area I'm working in. I've been training federal churches in the US understand numbers. If you think they have any training, no. They're even less than doctors. So here's a situation. Assume you are accused of having murdered a person. We do have no evidence against you except that your DNA matches on the traces on the victims. So, and I'm the judge. I'm innumerate, as most judges. And I call an expert witness to explain what this match means. And now it all depends how the expert witness frames the message. And at the end, it's two different conditional probabilities. So the expert witness might say, Your Honor, the probability that this match occurred by chance is 1 in 100,000. That doesn't look good for you. Agree? Ready for prison? So, what I'm teaching judges is to ask expert witness for frequencies. That's also a single event probability here. The probability that this match occurred by chance. So, the same expert witness would now phrase it differently and say, or answer the question, what does this match mean? And say, Your Honor, out of every 100,000 people, 1 will show a match. Now, in this city, there is 1 million, so 10 will show a match. In Berlin, we have 3.5 million, so 35 are expected. But it doesn't look any bad anymore for you. So the first probability, if you look closely, is both a single event probability, but it's also a probability that this match occurred by chance. That's the hypothesis, yeah? Given the data. While the other phrasing is 1 out of every 100,000 people, 1 shows a match. It's the probability of the data given the null hypothesis. So here we have the same confusion here. And whatever you do, insist on frequencies. And if you ever stay in trial, insist on frequencies, that the prosecution reports frequencies. Otherwise, you're doomed. And there are many cases documented in the US, in the UK, where where someone has confused the judges and the jurors, and then later, only later, one found out about that. And so, let me explain this now, what it does with health. Assume you are doing a mammography screening. And all what you know, what I'm doing now, I give you an example from when I teach doctors in continuing medical education. And this is from an example with gynecologists only. And I first give you the information in conditional probabilities, and I hope that I can produce fog in your mind. It's a sophisticated audience here, but it may nevertheless work with. And then I give you the same information, natural frequencies, and I hope the fog is dispelled and you see through. That's the point, the exercise. Ready? Okay. So you're doing a mammography screening, and all what you know is that the base rate of breast cancer, precisely undetected breast cancer, in that group is 1%. The probability that a woman will test positive if she has breast cancer is 90%. The probability that a woman will test positive if she does not have breast cancer is 9%. So you have a prevalence of 1%, a sensitivity of 90%, and a false positive rate of 9%. Now here a woman randomly comes to you and says, I just tested positive. Doctor, tell me, do I have breast cancer? Or what's the chance? Is it 99%, 90, 50, something else? What do you tell her? You know nothing about this woman. It's screening. What is your best estimate? If you now feel fog in your mind, that's exactly what I want to see. And by the way, you also are in the same situation as gynecologists. You should know it. Has anyone an estimate? 10%? Who was that?
I said that. Didn't you say there was a 9% false positive rate
Yes.
and a 10%, or and a 1%?
Yeah.
So she had a 10% chance of getting a positive result
How did you get there?
by adding the 1 and the 9.
I think this is a brilliant art to find the right answer with the wrong method. Okay. I show you first. I show you first. I take one continuing medical education session I conducted with 160 gynecologists. This was at the very beginning of there. And this kind of problem is something like that's their everyday business. They should know that. They should know the answer by heart. Or if they can't, they should be able to do some arithmetic. Arithmetic, not exactly yours, but so I gave them 4 alternatives. This is like a telesystem. They were as far as away you can think. So that the chance that she actually has cancer after testing positive is 1%, 10%, 81% or 90%. I took the 81% because there are other doctors who do a different kind of calculation than yours. They take the 90% and deduct the false positive rate. So they get 81. So what do you think? What's the distribution over these 4 alternatives among gynecologists? I'll show you. Every point is one gynecologist. There are 160 points. Almost half of them, 47%, think the answer is 90%. So the woman has most likely breast cancer. 13% think it's 81%. 21% think it's 10%. And 90% think it's 1%. Whatever the correct answer, you see the failure of medical school. It's all over the place. And the majority thinks it's more likely than not. Now, I'll now teach you a method that's called natural frequencies. That can resolve this fog. And the first step is you don't think about one particular woman, but you start with a class. It's about frequencies again. So to make it simple, let's start with 100 women. And then we translate these numbers. So we have 100 women who go screening. And we expect that one of them has breast cancer. This was the 1%. And we expected that this one woman most likely tests positive. That's the 90% sensitivity. Oh. And among the 99 who do not have breast cancer, we expect another 9 to test positive. Total, we expect 10 to test positive. How many of them do have actually breast cancer? You see it 1 out of 10. Yeah? And even gynecologists get it after 90 minutes being trained in many things. And at the end, I did not mention the solution for that problem. I gave them the same problem in this conditional probabilities again, and you can see that 87% could now translate it. There are a few hopeless cases up there, but you can't do everything in 90 minutes. But it illustrates that you can teach that for most people in short time. And as it is today, they haven't learned it. So what you have just done is called in statistics Bayes' rule. So the rule that's ascribed to Thomas Bayes. And it is, I show you now how this works, what it just did. So that's the conditional probability. In order to calculate the posterior probability, so the positive predictive value from the conditional probabilities where you had your fog in your mind, you would have done this calculation. So this is, you take the base rate, 1%, 0.01, multiplied with the sensitivity, 0.9, divided by the base rate, 0.01, multiplied by the sensitivity, plus the inverse prevalence, 0.99, multiplied by the false alarm, and then you calculate it. So that's the reason why you had fog in your mind, because it's a little bit hard, isn't it? Yeah. The interesting thing is natural frequency. So that's what you saw before. So 10 have cancer, 9 test positive, 1 negative, and so on. They facilitate the entire computation. And you have here that 9 out of all who test positive, so in this case it's almost 100, that makes everything easier. And if you want to understand it precisely, you don't have to multiply the base rates, the prevalence, with the condition probabilities anymore. Because this is the way like humans before statistics would have encountered information, just cases. And the probabilities over there, that's the base rates, and then they are normalized here. And here it's just, you have 1,000, and then the 990, and this adds up to 1,000. That doesn't add up to 1 here. And that makes everything just a little bit more difficult. So this is a simple way to understand base. And you can apply that to many situations, that everything has to do, to pregnancy tests, to tests in your own situation, or to HIV tests. Yesterday someone asked about HIV tests, so I put in a slide with HIV tests, whoever that person is. So let me first try to put fog in your mind again. Okay? And your task is then to unfog yourself. It's a little, just to get training. Okay. HIV screening, which means for people who have no symptoms. And it's the case in California. I think that for instance, pregnant women are asked to do HIV screening. That's at least what I learned from a Californian assistant professor who wrote me a letter thanking that she now understood the chances, what it means to get a test. So she was one of these unlucky women who were asked to do a test. She was pregnant, newly married, and she went to a testing center, and the test was positive. So she got the news on the phone, as typical, and the doctor told her, "You better tell your husband now." And in her letter to me, she wrote, "This was the worst evening of my life." She had no reason to assume that she was HIV positive, that she was infected with HIV. She had no reason to assume that. So she told her husband about the diagnosis, and then she remembered an article that from our research, where we had spelled out what it means. What's the probability that you actually have HIV if you test positive? And this is why it's important. She went with her husband to a different center, did a quick test, both negative, to another center, did another quick test, both negative, and then she stopped. But if she would taken this verdict seriously, she might have ended up with drugs that made her life and quality of life very difficult, but she would have survived and may have attributed the survival to the drugs. See that? And we do not know how many false positives are treated this way. So I'll show you now. Oh, I wanted to confuse you first. So let's do the following. You have a screening population, people who go, say pregnant women here in California, who go screening. Let's assume, to make numbers simple, that the prevalence of HIV, of undetected HIV in that group is 1 in 10,000. That's roughly so. The test is quite good, so the entire sequence of ELISAs and Western blots, but make the numbers also simple. So the probability that someone would test positive if she has HIV is 99.9. And the probability that she would test negative if she would have no HIV is 99.99. So that's the complement to the false alarm rate. This is excellent tests, but the numbers, they depend on whether it's a quick test or something else. We just get it. So, and here's a woman who tested positive, like in that case. What do you tell her? What's her chance that she actually is infected given a positive test when the prevalence is 1 in 10,000, the sensitivity is 99.9, and the false alarm rate is 0.001. No, 0.01. So 1 in 10,000. So fog in your mind? Yeah. Now translate it into natural frequencies. So here's it goes. So you think about, say, 10,000 clients, or women in this case. So one of them is expected to be infected. This one tests positive with practical certainty. That's the 99.9. On the other hand, there are 9,999 who do not have HIV. And we expect out of them, since the false positive rate over there is 1 in 1,000, so that one will test positive, and the others are likely. So you end up with 2 who test positive, and one of them has HIV, the other one not. Well, that's a very simple way to understand what's going on. And that actually was the calculation that helped these women to understand that it's not certain, as doctors told her, that she is infected with HIV. And again, you see the same thing, that space rule here. And if you had fog, that's the explanation why we had fog in your mind. And here, that how it simplifies the entire calculation. You can play around now and have a test that has maybe even a smaller false positive rate or anything else, but it's a general method to understand what's going on. We did 2 studies with HIV counselors to find out whether they understand their own tests. They were both done in Germany. And they were both undercover studies. So I am lucky to have many brilliant students, but sometimes also a courageous student. And this student was 25 years old, and we took a random sample of HIV counseling centers in Germany, 20 in that study, and he went to every one of those and said what he is, 20-year-old young man with an average sexual life. But he had heard of this test and he wanted to see what the result is. And during the counseling session, he asked the critical question. So, if one is not infected with HIV, is it possible to have a positive test result? That's the question about false positive. That's the big problem here. I show you now what these 20 counselors said. Most of the counselors are physicians, some are social workers. The first one said, no, certainly not. That's called the illusion of certainty. It's possible. Yeah? The second one said, absolutely impossible. This next one, with absolute certainty, not. No, not, never, never. Only number 10 had a more qualified answer. And he said, you can get this in France, but not here. And there were a number of qualified answers. For instance, that was done, so one counselor in Berlin who was old enough to have been there before the wall fell, explained that, it's all this problem now. When the wall was up, that functioned like the condom, and we were safe, but no longer. So That's the philosophy of something. And then false positives never happen, the same kind of illusion of certainty, no, no, no. And here was a group that were interesting. So the client, my student, was instructed, he did a semi-systematic interview. If he got one of these no, absolutely no, to ask again, did this never happen? And they all said, no, never, never. They changed their mind. Definitely not. When they ask again, they are extremely rare, which is true. And so absolutely not. And they came up with specificity numbers. And the rest, only these four, immediately said, it's not perfect, and except the last one, who was in a small town in Bavaria and insisted that the patient should trust him. I'm doing this since 20 years, just trust me. Client asked again, could it ever happen? Just trust me, no comment. That's another thing. So what you see here is that even the professionals have an illusion of certainty. And I'll show you just one example. I take this one, 99% specificity. So one of the better one who immediately came out that there could be a problem. And if you look closely at the protocol of this meeting, then you see something very interesting. I think there's a problem here with the resolution. Okay, it says, if one is infected, is it possible to receive a negative result? That's the other error. So that is, he's good on that. Then the critical question, if I'm not infected, can I get a positive result? That's here. And he says, if you take the test here, including confirmatory test, that's the Western blot, the test is extremely certain, and that's the specificity of 99%. Then he goes on, he asks about the base rate. Oh, and I'm sorry about that, what's down here, but I can tell you what's down here. That's the point, Then he asked about the PPV, so the positive predictive value. And the client and the counselor says, as I said before, let me hear, it's 99.9%. So he gets the specificity right, but confuses it with the other conditional probability, with the positive predictive value. And that's a very widespread thing in this.
When you have a number like 99.9%, I mean, is that really a verifiable, accurate number?
It has its margins of, so every test has its own specificities, and then it depends. That's usually taking the entire sequence of one ELISA, another ELISA from different manufacturer and a Western blot. Then some do the entire sequence one, so others do it also on a second blood test. And in the case of this young assistant professor from California, she told me that they only did the Western blot. They said, why would we do the ELISAs? If the Western blot is the better and more expensive one, let's just do that one. So the answer is there is really no standard procedure that's being done. And that's,
it's just that it's so close to 100%.
Yeah, that doesn't help you if the base rates are so low. That's the problem. And if you have a base rate of 1 in 10,000 and a false positive rate of 1 in 10,000, you have a 50-50 situation. You get one right and one wrong. That's easy to see. And if you have a base rate of 1 in 1,000, and so you can basically play wrong and know that. Yes.
I mean, is 100% within the error of the test?
So the best HIV tests, and there are among the best ones that we have, so the claim is that there are some of these tests where the false positive rate is not 1 in 10,000, but 1 in 250,000. Now I give you a homework. Use what you learned, do it in natural frequencies, and figure out what the positive predictive value is. So you start, you start not with 10,000, but with 250,000, and get down how many are there who actually do have, that would be in these numbers 25. And then you get one false positive, so you have 26 who test positive. And that's, still then, with such a brilliant test, out of 26 people, there's one false positive. And that's the way, if you train this a little bit, you can do it in your mind. Yes.
So what you're saying is the less likely there is a natural occurrence of the phenomenon, the more likely the test is to be false, irrespective of the methodology of the test. Just because of the base rate being so low, the test itself becomes more uncertain. Not because of the test, but because of the fact that the base rate itself is so low.
Yeah, the positive predictive value is then, it's basically, in this situation, look at the base rate and look at the false alarm rate. And if they're equal, you have roughly a 1-to-1 situation. And if one is 10 times as high as the other one, then that's exactly the thing. And this is why HIV screening is a problem. Because the danger is it creates lots of false positives. And we had that. It has benefits, but also these false positives. And one needs to be, the best thing is education, that people know about that. And it's not so difficult. So these techniques about natural frequencies are now in Germany taught in schools. So in the school plan, natural frequency is part of it. So every 11th grader learns that. That's new. That's since a year, where some of my students have shown that. So they are learning Bayes rule, but they're learning Bayes rule in the way with conditional probabilities. And when they do this, the tests have shown that 10% understand this. And when they were given these natural frequency trees, which they had never seen before, then most of them understand it. And that convinced the Ministry of Education, and they put it into as a requirement into the plans. So we can't change things. We just need to work on it. And towards the end, I show you this is a request by one of my new friends. The South Korea's thyroid cancer epidemic. Have you heard about that? South Korea is a concept. They have, since about the year 2000, the early 2000s, a steep increase in thyroid cancer diagnosis. Here are the facts. What you see is, first, this is per 100,000 population. Thyroid cancer is something that used to be extremely rare, so in the 1990s. And here, so in the early 2000s, it just got up. And it's now many factors more. What could cause this epidemic? What do you think? Screening, yeah. Screening, correct. And it's not mandatory, as you might think. It's not even recommended in South Korea, but some of the doctors have found ingenious solutions. They sell cancer screening as a 6-pack. You pay for 4, you get 6 of them. Until your thyroid cancer goes in. And the incidence curve is here, and the other curve below, this is a well-known version of thyroid cancer, which is basically irrelevant. Sorry. The problem is that in Korea, almost everyone who is diagnosed is immediately treated. So lots of anxiety is produced, and now an emergency. And sometimes it goes well, but sometimes they can lose the voice. through the operation or have other things, and most of them will be on hormones for the rest of their lives. And there is no firm data, but there is a suspicion that the debilitation late in life will progress and you will not live as long. So that's basically. And it's a case of overdiagnosis and overtreatment. How is this being sold? So in Korea, I had the luck having a Korean doctor joining my research group for a year, and he was studying what's happening in Korea. So this is an advertisement in a subway in Korea. It shows you the fast way by station on the subway to your thyroid. Yeah, that's the way you go. And thyroid cancer is now the most frequent cancer in South Korea. The costs are huge, and lots of techniques are sold, like robotic surgery, and 1 to 10%, the estimated number, experience harms from treatment, vocal cord damage, problems with calcium regulation, heart disease, stroke, osteoporosis. What happened in 2014, so when this was already up there, 8 South Korean doctors formed a physician coalition for the prevention of overdiagnosis, not of thyroid cancer, but of overdiagnosis of thyroid cancer, and proposed that screening should be discouraged. This group of 8 courageous, evidence-based doctors changed everything and stopped at least the increase. It's now flat. And broadcasters ran hour-long investigative programs on TV. Surgeries decreased by 25% within a year. And in 2015, the Korean Committee for National Cancer Screening guidelines that screened for thyroid cancer is not recommended for healthy subjects. So a small group of physicians can make a difference. There are a few more countries which also have thyroid cancer epidemics. One of them is the US. Another one is France. Another one is Italy in Europe. And where a group of doctors just promoted screening against the evidence and against the, I don't know whether they sell 6-packs here, but you see the same thing. The incidence is going up. It hasn't reached the rates in Korea. And the thyroid cancer mortality, which you see down here, has not changed at all. It's anyhow a very rare cancer. We have no evidence that it helps, but it hurts many. And much money is taken out of healthcare, which should be spent elsewhere. The promotion in the US goes, as usually, by celebrities. And here are 2 of the culprits, Brooke Shields and Cindy Crawford, who all hold her hands here to show the concern with the thyroids and are willing just to go along. Probably they get a big honorarium for that, doing that. And Light of Life Foundation is one of the foundations that promote check your neck. And and here's some information in the the award-winning television, print and radio campaign generated pro bono placements in publications including Time, InStyle, Everyday with Rachel Ray, Newsweek, and so on. So it's a massive advertisement campaign that's being done here. So, I'm coming to the last section. Are you still in good shape? Gary told me that he wished I should talk without any break. I said I need also a break at some point. Yeah. You get your prostate break. And the last thing, I'll just talk about a few tools in order to get the program running. First, I show you a test we did at the Charité which has 10 concepts. All of them I talked about here. What is sensitivity? What is specificity? What's the positive predictive value? Negative predictive value? Prevalence? That's a Bayesian task, the mammography task. What is a relative risk compared to an absolute? Mortality rate, lead time bias, overthinking. We had all this program. And they had multiple choice, 4 alternatives. They didn't have to define it, only to pick the right one. You get 25% correct. Look at the blue bars only, and you can see, if you average that out, on average they got 50% right. Every beginner in medical school, every first semester should understand these basic concepts. These are students at the end of medical school, and they get only 50% correct. So they will not be able to read an article in their own field and critically evaluate it. Then we did a 90 minutes training about various aspects, and these are the green bars. And it's just another demonstration. You can teach medical students, understand, you can teach them thinking, and at least they were tested 90 minutes after this invention, then most of them got it. The hardest things before training were so Bayes rule, and also to understand the difference between mortality rate and the 5-year survival rate. And that increased somehow after training. That increased really. They learned natural frequencies here. That really helped them. And this is just an illustration what we could do. At the end, I show you a few fact boxes. You have seen the mammography screening fact box. This is a fact box without numbers for those who don't like numbers or fear numbers. And it has the same structure, though the studies with over 300,000 men are broken down in every 1,000 who participate and every 1,000 who don't participate in screening. Okay, something has happened to my slides. Yeah. Strange how this can happen. Okay, I tell you what to ignore. So the point is, so these are 1,000 men with screening. These up here, the red ones with the P, these are those who die within 10 years from prostate cancer, and that's the same number here and here. So this is a summary across all available studies at this time. So here, if you only look at the European study, you would find one difference. But this is about all of them. These are, the red one are all men who die from any cause, and it's exactly the same. So these are men over 50, this is why relatively dead. The yellow one are the happy ones. And here some of these have, ignore all the red ones in that thing. Yeah? They somehow jumped in. And so the blue ones are those who actually have harms from going to screening. Those here are men who do have prostate cancer, but a non-progressive version. We talked about that before. That they never notice during their lives, but it's being detected, and they get prostatectomy or any kind of treatment, and about half of them will end up incontinent and or impotent. And the rest of these blue ones, blue light ones, these are men who do not have prostate cancer, but get a false alarms, test isn't good, and with the usual anxieties, unnecessary biopsies. And it's particular a problem for men because in mammography, one knows where to put the needle in order to do a biopsy. With a blood test, you have no idea where to put the needle, and many men get many needles until the thing has been found. So this is another way to explain what's going on, and using a fact box that has no numbers in it. And again, all of these fact boxes look up at the Harding Center for Risk Literacy. And here is another fact box on ovarian cancer screening, and which we do together with the largest health insurer in Germany, that's the AOK. And that's in electronic means. It's also in English available, and also in Turkish and other languages. And it has a design which is mixed, where you have numbers and then icons. So it is, the key line is up there, no benefits. Anal ultrasound examinations do not reduce the risk of dying from ovarian cancer. Here the exact number, out of 1,000, 3 die from cancer, 3 die from ovarian cancer, whether they do these tests or not. But the big difference is among those roughly 100 who test positive, who have a suspicious result. And unlike mammography, there is no way to do a biopsy, and one can only take the ovaries out, but not in again. And these studies show that out of 100 women who get a suspicious result, 94 are healthy. Well, that's the false alarm rate. 94 are healthy. And women should be told that, because otherwise they're getting excited. And also, those women here, out of these 100 here, about over 30 of them are such an anxiety that they're willing to have their ovaries taken out just to be sure. And then they get the good news and are glad and suffer for the rest of their lives. This screening is not recommended in Germany. The German doctors earn 38 euros from that, causing this amount of disaster for women. And women don't know. Here's a fact box on colon cancer early detection. This is the FOB test. And you can see the results are quite similar as mammography screening. There are 1,000 people without screening, 8 die from colon cancer, and here it's 7. It's again 1 out of 7, 1 out of 1,000. Yeah? The total mortality is exactly the same, and here are the harms. So that's how many people without cancer experience the false alarms. So that's about 20, and these are those who had a major complication. That's rare, that's less than 1. But again, it's a way, this should be in every doctor's office available, so that people finally understand the evidence. This is just a summary statistic of what we have done. And the final thing I wanted to share with you is a claim that I made on YouTube and other things. The claim is health literacy taught in school could save more lives than cancer screening and cancer medication together. The point is, explain you this calculation roughly. About 50% of all cancers are due to behavior. This is a very inexact estimate. We don't know. Could be a third, could be 2/3. So cigarette smoking ahead, estimated 20 to 30%. Obesity, physical inactivity, alcohol abuse, and all these 3 behaviors and habits are set early in life. And we need to enter there and try to make young people risk savvy before they enter puberty, and then develop habits from smoking, drinking, physical inactivity, and just eating the wrong kind of food. And here is a list of cancers, how they are linked. So cigarette smoking not only causes cancers of the lung, but also bladder, and also so-called second-hand cancers. Obesity and inactivity has many consequences. Alcohol abuse is still more a problem for men than for women. And also in the US, this figure is CT scans are estimated to cause 2% of all cancers. Again, a very rough estimate. And many of the CT scans are unnecessary. One study estimates that in the US, every year, 1 million children get unnecessary CT scans. And the reasons are either parents are overly anxious, the boy just fell, we want to be sure, or physicians make a business out of it, or physicians practice defensive medicine. They protect themselves against the parents that they might sue them. And okay, if the child then develops cancer 30 years later, that's no longer their business. And so the point here is I strongly believe if we would change the schools and teach health literacy in a playful way and change the habits of young kids, show them, for instance, a smoker lung, how it looks like, or how they will be when they enter puberty, will be misled by advertising into drinking, smoking, and so on, then we could do more and save more lives compared to the entire cancer screening, billions wasted there, and also to the, at the moment, the development of new drugs. Here's something where we can change something, but here's something where we don't invest. So,
can I ask a question about the CT scan?
Can you? You can, yeah?
Because I can understand that you can calculate the risk for obesity or smoking, because that goes on for a long time. But how can you say now that young children, 2% of them, will have a chance of cancer 30 years from now?
Okay. This is, do you see the references down here? Go into the Brenner and Hall study, and they explain how they're comparing it. These are estimates. These are estimates. Nobody can exactly predict that.
Another word for estimate is guess?
No. They are data. They often rely on data from nuclear bomb victims and trying to measure what the radiation doses they got. And then they calculate the radiation doses from CTs, which is in the order of 100 mammograms, depending on what organ is. And so they do these estimates. But they are estimates. That's true. So let me finish here. In this first lecture, I was concerned with health literacy among doctors and patients. And we could increase their number if we would start teaching risk literacy in medical school and continuing medical education. It's not happening. Continuing medical education in the US, like in Germany, is in the hands of the industry, of the pharmaceutical industry mostly, and interest on that side is limited in doctors who are risk literate. And second, we need to do something to make sure that information in journals, in pamphlets, and in the media, that the amount of misleading statistics is reduced and clear statistics is introduced. And finally, I've not talked much about that here. Innumeracy is not the only problem. We live in a healthcare system that is full with conflicting interests, where there's so much money that so many people are more interested in the money than in the patients. And also there is the big problem of defensive medicine, given the American tort law. And many physicians, they just try to protect themselves against the possibility they're being sued. And what we would gain by this program is we would have better doctors, better patients, and better healthcare. Thank you for your attention.